Messier 87, a massive elliptical galaxy at the heart of the Virgo cluster, has long been a subject of fascination for astronomers. Known for its supermassive black hole, which became the first ever to be imaged in 2019, M87 is a cosmic marvel that offers invaluable insights into the nature of black holes, galaxy formation, and the mysterious forces that shape our universe. From its powerful jet of particles to its vast dark matter halo, this galaxy holds the key to understanding some of the most fundamental aspects of astrophysics. In this video, we'll delve into the mysteries of Messier 87, exploring its origins, its black hole, and the groundbreaking discoveries that continue to redefine our understanding of the cosmos. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Messier 87 is not just another galaxy catalogued among billions. It is an ancient cosmic leviathan that has silently sculpted the environment around it for billions of years. Discovered over 2 centuries ago, M87 is a galaxy that continues to intrigue and baffle astronomers, physicists, and cosmologists to this day. Nestled within the Virgo cluster, approximately 53.5 million light-years away from Earth, M87 stands out due to its staggering size, fascinating structure, powerful relativistic jet, and perhaps most notably its supermassive black hole, the first ever to be directly imaged by humanity. To even begin to appreciate the grandeur of M87, one must first attempt to wrap their mind around the colossal scales involved. M87 is classified as a giant elliptical galaxy, meaning it lacks the spiral arms that we associate with galaxies like our Milky Way. Instead, it is a sprawling, somewhat amorphous cloud of countless billions of stars. The very appearance of M87 is deceptive in its simplicity. From afar, it looks like a relatively featureless ball of stars, but lurking within and around it are countless cosmic phenomena. The diameter of M87 extends well over 120,000 light-years, comparable in size to the Milky Way, but its mass tells a different story. While our home galaxy contains several hundred billion stars, M87 is thought to contain as many as several trillion stars, along with countless globular clusters and an extraordinary amount of hot gas. The mass of M87 is simply staggering, estimated to be several trillion times the mass of our Sun. The true heart of M87, however, is not its stars or its globular clusters. It is its central supermassive black hole, a behemoth that tips the scales at a mass of around 6.5 billion solar masses. This black hole was thrust into the public consciousness in April 2019 when the Event Horizon Telescope collaboration unveiled the first ever direct image of a black hole's event horizon, and that black hole was M87's. The image showed a glowing ring of light surrounding a dark central shadow, a visual confirmation of decades of theoretical predictions. This moment marked one of the most significant milestones in the history of astronomy and physics, forever tying the name M87 to human scientific achievement. Yet, the story of M87's black hole is not merely one of mass and size. It is an active supermassive black hole, devouring matter at an incredible rate and producing one of the most powerful and spectacular phenomena in the universe, a relativistic jet. Stretching for thousands of light-years, this jet is composed of material accelerated to nearly the speed of light, spewing forth from the region around the black hole and extending deep into intergalactic space. Observations of M87's jet have provided crucial insights into the mechanics of black holes, the nature of relativistic particles, and the ways in which galaxies can influence their environments across cosmic scales. To understand M87 in its entirety, however, we must look beyond the black hole and the jet. We must peer into its structure, its population of globular clusters, its role within the Virgo cluster, its history of mergers and accretion, its dark matter halo, and its significance in the broader context of cosmic evolution. We must explore the theories and models that seek to explain its formation and behavior. We must dive into the techniques and technologies that have allowed us to observe and study this distant giant. Only by doing so can we hope to paint a complete picture of this extraordinary galaxy. The history of M87's discovery dates back to the late 18th century when French astronomer Charles Messier compiled a catalogue of nebulae and star clusters to aid comet hunters. M87 was listed as the 87th entry in his catalog, and at the time, its true nature as a galaxy was unknown. It appeared as a fuzzy, featureless patch of light through the telescopes of the era. It wasn't until the 20th century, following Edwin Hubble's revolutionary work in the 1920s, that astronomers came to understand that such nebulae were actually distant galaxies outside the Milky Way. M87, being relatively close in cosmic terms and extraordinarily luminous, quickly became a subject of intense study. Over the decades, increasingly sophisticated observations across the electromagnetic spectrum, from radio waves to X-rays, have peeled back the layers of mystery surrounding it. Each wavelength reveals different aspects of M87's nature. The radio observations show the vast jets and lobes. Optical observations reveal the stars and globular clusters. X-ray observations expose the hot gas permeating the galaxy and its surroundings. One of the striking features of M87 is its rich system of globular clusters. These densely packed groups of ancient stars orbit the galaxy in great numbers. While the Milky Way boasts about 150 to 200 globular clusters, M87 possesses a staggering number. Estimates suggest as many as 12,000 to 15,000. This population is not merely a trivial statistic. It provides crucial clues about the galaxy's history. The sheer number and distribution of these clusters imply a tumultuous past filled with mergers and accretion events, whereby M87 grew by absorbing smaller galaxies over billions of years. The hot gas surrounding M87 and filling much of the Virgo cluster is another testament to the galaxy's influence. This gas emits strongly in the X-ray part of the spectrum and is held in place by the gravitational pull of the galaxy and the cluster. Observations have shown that the interactions between M87's jet and the surrounding gas create shock waves and cavities, influencing the temperature and distribution of the gas on enormous scales. These interactions are crucial for understanding the life cycle of galaxies and clusters, as they regulate star formation and the growth of cosmic structures. M87's role within the Virgo cluster is that of a dominant central galaxy, often referred to as a CD galaxy, a classification denoting a supergiant elliptical galaxy at the center of a galaxy cluster. It exerts a profound gravitational influence over its surroundings, and its mass accounts for a significant portion of the cluster's total mass. The dynamics of the Virgo cluster, including the motion of its member galaxies and the behavior of the hot intracluster gas, are heavily influenced by M87. The formation of M87 is a story written over billions of years, involving countless mergers and accretion events. In the early universe, smaller galaxies would have coalesced to form larger structures, and through successive mergers, M87 grew to its current size. These events left their imprint on the galaxy's structure and stellar population. Unlike spiral galaxies, which can retain orderly rotating disks, giant elliptical galaxies like M87 are more randomized in their stellar motions, a direct result of these chaotic pasts. Understanding M87 also requires an exploration of the elusive dark matter that envelopes it. Dark matter, the unseen mass that does not emit or absorb light, is thought to make up the bulk of the galaxy's mass. Studies of the motion of stars and globular clusters within M87 revealed the gravitational grip of an invisible halo far more massive than the visible components of the galaxy. This dark matter halo plays a crucial role in the dynamics of the galaxy and the cluster at large. The observation and study of M87 have been propelled by technological advances that push the boundaries of human ingenuity. Ground-based observatories like the Very Large Telescope, VLT, and the Atacama Large Millimeter/Submillimeter Array, ALMA, along with space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory, have provided invaluable data across multiple wavelengths. The Event Horizon Telescope, a global network of radio observatories, synthesized its data to produce the groundbreaking image of M87's black hole, a feat that required the coordination of facilities across the planet and sophisticated data processing techniques. M87's jet, an iconic feature visible in radio, optical, and X-ray images, is a subject of intense study. The mechanisms behind jet formation are complex and involve the interplay of magnetic fields, accretion disks, and the rotation of the black hole itself. Models suggest that material spiraling into the black hole forms a disk, and the intense magnetic fields associated with the disk and black hole can funnel some of this material along the poles at relativistic speeds. The jet stability, structure, and interaction with the surrounding medium provide crucial insights into these processes. The importance of M87 in the broader context of astrophysics cannot be overstated. It serves as a natural laboratory for studying the physics of black holes, the dynamics of jets, the behavior of hot gas and clusters, the role of dark matter in galaxy formation, and the evolution of massive galaxies. Each observation of M87 brings new insights and often raises new questions, driving the progress of science. In contemplating M87, we are confronted with the vastness and complexity of the universe. This single galaxy encapsulates many of the most profound and challenging aspects of cosmology and astrophysics. It reminds us of how much we have learned, and how much more there is still to discover. At a distance of approximately 53 million light-years from Earth, Messier 87 resides within the heart of the Virgo cluster, a sprawling collection of over 1,000 galaxies gravitationally bound together in a celestial dance older than humanity itself. When we peer into the void toward M87, we are not merely looking at another point of light. We are peering back in time, gazing upon a galaxy whose light has traveled for tens of millions of years to reach us, carrying with it secrets of the primordial cosmos. Messier 87, often referred to simply as M87, was first catalogued by Charles Messier in 1781 during his ambitious quest to identify objects that could confuse comet hunters. Yet little did Messier know the nebula without stars he recorded as the 87th entry in his catalogue would later emerge as one of the most extraordinary discoveries in the annals of astronomy. At the time of its cataloguing, the true nature of galaxies themselves remained unknown. Humanity still believed that the Milky Way encompassed the entire universe. It was only centuries later, through the tireless efforts of countless astronomers, that M87 revealed itself not as a mere cloud, but as a sprawling giant galaxy, a universe within a universe. M87 is classified as a giant elliptical galaxy, one of the largest and most massive known to science. Unlike the elegant, swirling spirals of galaxies like our own Milky Way, elliptical galaxies such as M87 lack the distinct spiral arms that characterize their more photogenic cousins. Instead, M87 presents itself as an immense, featureless, roughly spherical halo of stars, gas, dust, and dark matter, extending outward across an expanse of space so vast that it dwarfs even the most prodigious structures known to us. Estimates suggest that Messier 87 contains more than 1 trillion stars, an astronomical number almost impossible to fathom with the human mind. Each of these stars may host its own systems of planets, moons, and cosmic phenomena, rendering M87 not just a galaxy, but a theater of infinite potential worlds, each dancing to the cosmic rhythms of gravity and time. And yet, even these staggering statistics fail to capture the full grandeur of M87, for its true claim to fame lies not merely in its mass or its size, but in the monstrous entity that resides at its heart, a supermassive black hole of unimaginable proportions. This black hole, which has been the subject of intense study and fascination, came to international prominence in 2019 when the Event Horizon Telescope, EHT, collaboration unveiled the very first direct image of a black hole's shadow. This groundbreaking achievement marked one of the greatest milestones in the history of science, as humanity for the first time gazed upon the silhouette of a cosmic titan that bends space and time itself. The image revealed a glowing ring of superheated matter encircling a dark central void, the event horizon, beyond which nothing, not even light, can escape. The black hole at the center of M87, known formally as M87*, is not merely large, it is colossal beyond comprehension. Current measurements suggest that M87* possesses a mass equivalent to approximately 6.5 billion times that of our Sun. To place this into perspective, if the black hole were placed at the center of our solar system, its event horizon would encompass the orbit of Pluto and extend far beyond. This is not merely a black hole, it is a gravitational behemoth whose presence warps the very fabric of reality in its vicinity. The environment surrounding M87* is a chaotic maelstrom of activity. Enormous amounts of gas and dust spiral inward toward the black hole, forming a brilliant accretion disk heated to millions of degrees by the immense gravitational forces at play. From the poles of the black hole, relativistic jets of matter are expelled at nearly the speed of light, stretching outward for thousands of light years into intergalactic space. These jets, composed primarily of electrons and positrons, are among the most energetic phenomena in the known universe, their sheer power capable of influencing the structure and evolution of the galaxy itself. The origin of these jets remains one of the most tantalizing mysteries in astrophysics. Despite decades of observation and theoretical modeling, scientists have yet to fully unravel the precise mechanisms by which black holes generate and sustain such colossal outflows of energy. It is believed that the intense magnetic fields generated by the accretion disk play a critical role, but many details remain elusive, hiding within the realm of relativistic magnetohydrodynamics and plasma physics, fields that challenge even the most sophisticated models humanity can devise. Beyond its central black hole, M87's massive size and unique properties continue to captivate astronomers. Its vast halo of stars is home to an extraordinary number of globular clusters, dense, spherical collections of ancient stars tightly bound together by gravity. While the Milky Way hosts around 150 to 200 such clusters, M87 boasts a staggering population of approximately 12,000 to 15,000 globular clusters, each a relic from the early epochs of galactic formation. These clusters serve as time capsules, preserving the chemical signatures and stellar populations of a universe far younger than the one we know today. Moreover, M87's position within the Virgo cluster situates it as a gravitational anchor for its surrounding neighbors. Its sheer mass exerts an influence across millions of light years, pulling nearby galaxies inward in a slow but inexorable migration toward eventual collision and merger. Over cosmological timescales, these interactions will transform the very architecture of the Virgo cluster, gradually building larger and more massive structures in the ongoing story of cosmic evolution. The study of M87 also offers profound insights into the nature of dark matter and dark energy, the enigmatic components that constitute the vast majority of the universe's mass-energy content. By analyzing the motions of stars within the galaxy and the gravitational lensing effects it produces, astronomers can infer the distribution of invisible mass within and around M87. These studies suggest that a vast halo of dark matter envelopes the galaxy, providing the necessary gravitational glue to hold its immense structure together. In addition, observations of M87 and its surroundings contribute to our understanding of cosmic feedback mechanisms, processes by which energetic events such as black hole jets regulate the formation of stars and the growth of galaxies. The jets emanating from M87* inject tremendous amounts of energy into the surrounding interstellar and intergalactic medium, heating the gas and preventing it from cooling and collapsing into new generations of stars. This feedback loop plays a crucial role in shaping the life cycles of galaxies, illustrating the profound interconnectedness between the smallest scales of black hole physics and the largest scales of cosmic structure. The saga of M87 is a testament to the power of human curiosity and the relentless drive to explore the unknown. From the rudimentary telescopes of the 18th century to the vast arrays of radio dishes spanning continents, our quest to understand this galactic giant has pushed the boundaries of technology, mathematics, and imagination. Each new discovery peels back another layer of mystery, revealing deeper complexities and inviting ever more profound questions. As we continue our journey into the depths of M87, we must pause to consider the philosophical implications of such exploration. What does it mean that in the vast emptiness of space, a single galaxy can harbor forces so immense that they defy comprehension? What does it say about our place in the universe that we can, through the fragile instruments of our own invention, glimpse the invisible, touch the intangible, and measure the immeasurable? In seeking to understand M87, we are, in a very real sense, seeking to understand ourselves, our origins, our destiny, and the nature of the reality we inhabit. The story of Messier 87 is not just a tale of stars and black holes, it is a story of transcendence. It is the story of how a species born of dust on a tiny blue world looked outward, reached beyond the confines of its cradle, and dared to imagine the unimaginable. It is a story that will continue to unfold for generations to come, as new instruments, new theories, and new minds rise to meet the eternal challenge of the unknown. Even now, as we stand on the precipice of new discoveries, M87 beckons us onward. With future telescopes such as the James Webb Space Telescope, the Extremely Large Telescope, and the next generation of the Event Horizon Telescope, we will probe deeper into its mysteries, capturing finer details of its structure, dynamics, and perhaps even catching glimpses of the turbulent regions just beyond the event horizon of its central black hole. But for all our future advancements, one truth will remain: Messier 87 is, and will always be, one of the grandest and most awe-inspiring spectacles in the universe, a beacon of mystery shining across the cosmic ocean, inviting us to dream, to wonder, and to explore without end. Astronomers devoted decades, even centuries, to unraveling the mysteries hidden within the light of distant celestial objects, and eventually, the veil lifted. It became clear that Messier 87 was not a nebula within the Milky Way, but a gargantuan elliptical galaxy, an island universe in its own right, situated far beyond the boundaries of our home galaxy. M87 contains hundreds of billions of stars, each weaving their own intricate stories across the canvas of cosmic history. Unlike the Milky Way, which is a grand spiral adorned with elegant arms and lanes of dust and gas, M87 presents itself as a featureless, sprawling elliptical structure. It lacks the ornate spiral architecture that captures the imagination when we think of galaxies, and instead offers something different: a colossal, spherical or elliptical ball of stars, globular clusters, and an unimaginable amount of mass lurking invisibly as dark matter. The stars within M87 are not arranged in orderly rotating disks. Instead, they orbit the galaxy's center in random directions, forming a complex and dynamic three-dimensional structure that challenges the simplistic notions of galactic symmetry. What makes M87 even more extraordinary is what lies at its very core: a supermassive black hole of staggering proportions. In 2019, the Event Horizon Telescope collaboration revealed to the world the very first image of a black hole's shadow, and the black hole they imaged resided not within our own Milky Way, but deep within the heart of Messier 87. This supermassive black hole, known simply as M87*, is estimated to have a mass equivalent to approximately 6.5 billion suns. It is so massive, so gravitationally dominant, that the very fabric of space-time itself warps and curves dramatically around it. The image captured by the Event Horizon Telescope was a landmark moment for humanity. It was the culmination of decades of theoretical work, technological innovation, and international collaboration, and it was M87 that gifted us this first direct glimpse into one of the most extreme phenomena predicted by Einstein's general theory of relativity. The silhouette of the black hole appeared against the glow of hot, infalling gas and plasma, forming a glowing ring around a dark center, the shadow of the black hole itself, a place where even light cannot escape. But M87's story stretches far beyond this singular achievement. The black hole at its center is not a dormant titan. It is active, consuming vast quantities of matter, and in doing so, it unleashes some of the most powerful and spectacular phenomena in the universe. M87 is famous for its relativistic jet, a narrow beam of energetic particles that is ejected from the vicinity of the black hole at nearly the speed of light. This jet extends outward from the galaxy's core for over 5,000 light-years, a structure so large that it dwarfs many smaller galaxies. Observed in radio, optical, and X-ray wavelengths, the jet is a living testimony to the violent processes unfolding at the very edge of the black hole's event horizon. Scientists believe that the jet is powered by magnetic fields twisted and amplified by the intense rotation of the accretion disk, the swirling disk of gas and dust spiraling into the black hole. As material falls inward, some of it becomes trapped in the magnetic fields and is hurled outward at relativistic speeds, forming a coherent jet that punches through interstellar space. Observations of M87's jet provide critical insights into the mechanisms by which black holes interact with their host galaxies and regulate the growth of cosmic structures. The presence of such a jet also indicates that M87* is an active galactic nucleus, AGN, though it is relatively low luminosity compared to the most energetic quasars found elsewhere in the universe. Nevertheless, the energy output from M87's core has profound effects on its surroundings. It heats the interstellar and intracluster medium, suppresses star formation by preventing gas from cooling and collapsing, and helps shape the evolution of the galaxy and the larger Virgo cluster itself. Beyond the black hole and the jet, Messier 87 harbors other marvels. It boasts a remarkable population of globular clusters, dense, spherical collections of ancient stars that orbit the galaxy's core. M87 is home to around 12,000 to 15,000 globular clusters, far more than the roughly 150 to 200 known in the Milky Way. These clusters are among the oldest known structures in the universe, fossils from a time when galaxies were just beginning to form. Studying M87's globular clusters provides critical clues about the early history of galaxy formation, the buildup of mass over cosmic time, and the mysterious nature of dark matter that binds galaxies together. The mass of Messier 87 is truly staggering. When we speak of its size, it is not merely a measure of its span across space, but also of the invisible weight it carries. The total mass of M87 is estimated to be several trillion times the mass of our Sun, making it a gravitational anchor within the Virgo cluster. Much of this mass is unseen, composed of dark matter, the enigmatic substance that neither emits nor absorbs light but reveals its presence through its gravitational effects. Dark matter forms an extended halo around M87, binding its stars and globular clusters and influencing the motion of neighboring galaxies within the cluster. Astronomers have utilized a variety of methods to measure the mass of M87 and its black hole, including tracking the motion of individual stars near the core, studying the dynamics of the globular clusters, and observing the behavior of hot gas-emitting X-rays under the gravitational influence of the galaxy. Each method converges upon the same conclusion: M87 is not merely large, it is a cosmic leviathan, a galaxy so massive that it shapes the fate of its entire galactic neighborhood. In the larger cosmic context, Messier 87 provides a crucial laboratory for understanding galaxy formation and evolution. It is believed that giant elliptical galaxies like M87 form through the mergers of smaller galaxies over billions of years. In these colossal collisions, stars from the merging galaxies are flung into random orbits, creating the smooth, featureless appearance characteristic of elliptical galaxies. M87's mass, size, and structure suggest a long and violent history of galactic cannibalism, during which it absorbed countless smaller galaxies, growing ever larger and more massive. Moreover, M87's place within the Virgo cluster ties it intimately to the broader structure of the universe. The Virgo cluster itself is a central component of the Virgo supercluster, which in turn is part of the Laniakea supercluster, the vast, interconnected web of galaxies that constitutes our local region of the cosmos. M87 acts as a gravitational anchor within the Virgo cluster, its immense mass helping to hold the cluster together against the expansion of the universe. Despite its incredible distance, M87 can be observed with modest amateur telescopes under dark skies, appearing as a faint, diffuse glow. It does not dazzle the eye like closer galaxies such as Andromeda, but knowing what lies within that faint smudge, a supermassive black hole, relativistic jets, ancient globular clusters, and the accumulated history of cosmic violence, transforms the experience of viewing it into something profoundly humbling. Even now, Messier 87 continues to be a focus of intense astronomical study. Observations across the electromagnetic spectrum, from radio waves to gamma rays, reveal new layers of complexity within this remarkable galaxy. Radio telescopes map the structure of the jet and probe the magnetic fields at the galaxy's core. Optical telescopes study the distribution of stars and globular clusters. X-ray observatories like Chandra investigate the hot gas that fills the space between galaxies in the cluster. Together, these observations weave a rich tapestry of knowledge, allowing astronomers to piece together the story of M87 across cosmic time. At the same time, theoretical astrophysicists use M87 as a testbed for models of black hole physics, galaxy formation, dark matter, and cosmic evolution. The successful imaging of M87's black hole by the Event Horizon Telescope validated many predictions of general relativity, but it also opened new questions about the nature of black holes, the behavior of matter under extreme conditions, and the fundamental structure of spacetime itself. The journey of discovery is far from over. As observational technology advances, future instruments such as the James Webb Space Telescope, the Extremely Large Telescope, and next-generation radio arrays promise to unveil even deeper secrets about Messier 87. They will peer with greater clarity into the heart of the galaxy, resolve finer details of the jet, map the distribution of dark matter with unprecedented precision, and perhaps even reveal the role of M87 within the grander cosmic web that connects all galaxies together. Messier 87 stands as a monument to the power of gravity, the violence of cosmic evolution, and the mysteries that still lie beyond our reach. It is a reminder that even in a universe filled with countless galaxies, some stand out as extraordinary, titanic structures whose stories capture the imagination and drive the quest for knowledge ever forward. At the very core of M87 lies a supermassive black hole of unprecedented proportions, one whose presence has captured the imagination of astronomers and the public alike. This cosmic monster weighs approximately 6.5 billion times the mass of our Sun, making it one of the most massive black holes ever measured. Its gravitational pull is so immense that it warps the very fabric of space and time, creating an abyss from which nothing, not even light itself, can escape once it crosses the event horizon. For many decades, astronomers suspected that M87's core housed a supermassive black hole. The evidence was compelling yet indirect, inferred from the rapid motion of stars and gas swirling around an invisible center. The stars in the innermost regions of M87 moved at astonishing speeds, defying any explanation other than the presence of a concentrated mass too dense and too small to be anything but a black hole. Yet direct observation remained a dream beyond reach, until a monumental achievement in human scientific endeavor changed everything. In April 2019, the world witnessed history. The Event Horizon Telescope, EHT, a planet-wide network of synchronized radio observatories, unveiled the very first image of a black hole's shadow. It was the shadow of the black hole at the center of M87. This image, a blurry but profound ring of golden light encircling a dark void, was a triumph of science, technology, and global cooperation. Never before had humanity glimpsed the edge of a black hole, and fittingly, it was M87's titanic black hole that first yielded its secrets. The EHT's success in imaging M87's black hole was no simple feat. Coordinating telescopes across continents, synchronizing them with atomic clocks, and processing petabytes of data through sophisticated algorithms was a task that pushed the limits of our technological capabilities. The final image was a direct confirmation of predictions made decades earlier by Einstein's theory of general relativity, showcasing the shadow, a dark region corresponding to the black hole's event horizon surrounded by the photon ring, where gravity bends and captures light into orbit. But the black hole itself is just one breathtaking feature among many within M87. This galaxy is also famous for another awe-inspiring phenomenon, its relativistic jet. Stretching across thousands of light-years into intergalactic space, this jet is a narrow, powerful stream of energetic particles accelerated to near the speed of light, propelled by the immense magnetic fields and gravitational forces around the black hole. The jet of M87 is so massive that it can be seen across the electromagnetic spectrum, in radio waves, visible light, X-rays, and gamma rays, and it provides critical insights into the behavior of matter and energy under conditions of extreme gravity. The jet was first observed in visible light in 1918 by astronomer Heber Curtis, who noticed a curious, straight ray extending from the center of M87. This discovery was revolutionary, challenging the prevailing notions about the quietness of elliptical galaxies and suggesting a dynamic, energetic process at play in M87's nucleus. Today, with the power of modern observatories such as the Hubble Space Telescope and the Chandra X-ray Observatory, scientists have mapped the jet in exquisite detail, revealing shock waves, knots of particles, and complex magnetic structures that continue to puzzle and inspire theoretical physicists. When considering the mass of M87's black hole, its influence extends far beyond its immediate surroundings. The black hole affects the galaxy's entire core structure, heating the gas, regulating star formation, and shaping the fate of the surrounding matter. This feedback mechanism, wherein energy released by the accretion of material onto the black hole affects the host galaxy, is a key concept in understanding not only M87 but galaxy evolution as a whole. M87 serves as a prime laboratory for studying these processes on the grandest scales. Yet the black hole, the jet, and the galaxy's visible features are only the beginning. M87 is steeped in mysteries invisible to the naked eye. Like most massive galaxies, it is believed to be enveloped by a vast halo of dark matter, an unknown, unseen form of mass that exerts gravitational influence yet emits no detectable light. Dark matter is essential to explaining the motion of stars within M87 and the gravitational binding of the entire Virgo cluster. Without it, the galaxy would fly apart under its own rotational energy. This dark matter halo extends well beyond the bright stellar body of M87, blending into the larger structure of the Virgo cluster itself. The interplay between M87's visible mass, its dark matter, and the surrounding intergalactic medium weaves a tapestry of gravitational interactions that define the large-scale architecture of our corner of the universe. Observations of M87, combined with simulations of cosmic evolution, suggest that such giant elliptical galaxies grew through a series of mergers and accretions over billions of years, devouring smaller galaxies and absorbing their stars, gas, and dark matter into an ever-growing, gravitationally dominant entity. The history of M87 is, therefore, a story of cosmic cannibalism on an unimaginable scale. Over eons, smaller galaxies fell into its grasp, drawn inexorably by gravity, shredded and consumed in gravitational dances of destruction and rebirth. The remnants of these ancient mergers can still be detected today as faint stellar streams, globular clusters with peculiar motions, and subtle distortions in the galaxy's outer halo. Each of these features is a fossil record of a collision, an event that shaped M87's growth and character. Globular clusters, in particular, provide critical clues about M87's past. This galaxy hosts an extraordinarily rich system of over 12,000 globular clusters, spherical collections of ancient stars bound together by gravity, compared to the Milky Way's mere 150 or so. These clusters orbit M87 in all directions, relics of a time when the universe was young and galaxies were assembling their first generations of stars. By studying the distribution, motion, and composition of these globular clusters, astronomers can piece together the complex history of mergers, accretion, and growth that built M87 into the Leviathan we observe today. The vast halo of M87, punctuated by its thousands of globular clusters, is itself embedded in an even larger environment, the Virgo cluster's core. Here, M87 reigns supreme as the dominant gravitational anchor, influencing the motion of other galaxies within the cluster. Smaller galaxies orbit it like moths drawn to a flame, their motions revealing the immense gravitational power M87 wields over its cosmic neighborhood. The study of galaxy clusters like Virgo provides crucial insights into the distribution of mass in the universe, both visible and dark, and M87 stands at the heart of these investigations. In addition to its optical majesty, M87 is a prodigious emitter of radiation across the electromagnetic spectrum. Radio observations, beginning in the early 20th century, revealed M87 as a powerful radio source, designated Virgo A. Its radio lobes, vast, balloon-like structures inflated by the energy of the central black hole, extend for tens of thousands of light-years, reshaping the intergalactic medium and providing a clear signature of the titanic energies at work in this galaxy. In X-ray wavelengths, M87 shines brightly as well. Observations with the Chandra X-ray Observatory have revealed a complex interplay between the black hole's activity and the hot gas permeating the Virgo cluster. Cavities, shock fronts, and ripples in the X-ray emitting gas betrayed the repeated outbursts from M87's nucleus over millions of years. These outbursts inject energy into the surrounding medium, preventing the gas from cooling and collapsing to form new stars, a process known as feedback that helps regulate the growth of massive galaxies. M87's importance to astrophysics cannot be overstated. It serves as a cosmic laboratory for testing theories of gravity, black hole dynamics, galaxy formation, and cosmic evolution. Its proximity relative to other massive galaxies allows astronomers to study it in exquisite detail, making it a cornerstone of observational cosmology. Yet despite all that has been learned, M87 still guards countless secrets. What precisely triggers the supermassive black hole's energetic outbursts? How do magnetic fields near the event horizon organize to launch the relativistic jet? What is the true nature of the dark matter that enshrouds the galaxy? These questions drive ongoing research and ensure that M87 will remain at the forefront of astronomical exploration for decades, even centuries, to come. As we continue our voyage deeper into the intricacies of M87, it becomes ever clearer that this galaxy is not merely an object of scientific inquiry but a profound symbol of humanity's quest to understand the cosmos. It reminds us that no matter how vast the universe, no matter how distant or mysterious its wonders, our minds, and our technologies, can reach across the abyss and touch the very heart of creation itself. The Event Horizon Telescope's accomplishment in capturing the image of M87's black hole represented one of the greatest scientific feats of the 21st century. It was a triumph that required extraordinary collaboration, involving over 200 scientists across multiple continents, working tirelessly to synchronize radio telescopes into a virtual Earth-sized observatory. This global network allowed astronomers to achieve an angular resolution so fine that it would be akin to spotting a single orange on the surface of the Moon from Earth. The image itself, with its hauntingly beautiful ring of light surrounding a dark central shadow, was not merely a photograph, it was visual confirmation of decades of theoretical predictions rooted in Einstein's theory of general relativity. The bright ring resulted from photons bent by the immense gravitational field of the black hole, forming what is known as the photon sphere. Within that ring, the darkness marked the event horizon, the point of no return, beyond which matter and radiation vanish forever from the visible universe. This monumental observation did more than just confirm theories. It opened an entirely new era in astrophysics. Scientists could now study black holes not only through their indirect effects on surrounding matter but also through direct imaging of their immediate environments. The black hole of M87, with its immense mass and relatively close proximity compared to other candidates, became the perfect laboratory for studying these mysterious objects that challenge our understanding of gravity, space, and time itself. Yet the supermassive black hole is not the only remarkable feature of Messier 87. Emerging from the galactic core is a colossal jet of plasma, a beam of energetic particles accelerated to near the speed of light. This jet stretches for thousands of light-years into intergalactic space, a breathtaking manifestation of the raw power unleashed by the dynamics surrounding the black hole. Astronomers had first noticed this jet in the early 20th century, long before the nature of black holes was understood. In optical images, the jet appears as a narrow, brilliant streak, while in radio and X-ray wavelengths, it reveals an even more intricate and expansive structure. The jet is powered by the interaction of magnetic fields and rapidly spinning material in the accretion disk around the black hole. As matter falls toward the event horizon, it becomes trapped in magnetic field lines, which twist and launch some of the material outward at relativistic speeds. This process, known as relativistic jet formation, is still not fully understood, but M87's jet offers a natural laboratory for its study. Observations across different wavelengths, from radio to optical to X-ray, provide insights into the jet's composition, structure, and the processes that energize it. The sheer scale and energy of M87's jet are mind-boggling. If it were visible to the naked eye in our night sky, it would stretch across the breadth of several full moons. Within the jet, shockwaves and knots of material indicate regions where particles are accelerated to even greater energies, producing intense radiation detectable across the electromagnetic spectrum. The study of these jets has implications far beyond M87 itself, touching upon the behavior of active galactic nuclei throughout the universe and influencing the evolution of entire galaxies. The existence of the jet also hints at the complex internal life of M87. Unlike our Milky Way, which is relatively sedate in its center today, M87's nucleus is a hub of frenetic activity, with continuous accretion of matter and the ejection of vast amounts of energy. This activity shapes not just the immediate galactic environment, but also the surrounding intergalactic medium. Observations have revealed that the central regions of the Virgo cluster are flooded with radio emission, a sign of the interactions between M87's energetic output and the tenuous gas that permeates the cluster. Beyond its active core and powerful jet, M87's overall structure tells a story of ancient cosmic collisions and mergers. As an elliptical galaxy, it likely formed through the gradual accretion of smaller galaxies over billions of years. The smooth, rounded appearance of M87 hides a tumultuous past filled with gravitational interactions, stripping of stars from infalling systems, and the eventual coalescence into the massive entity we see today. Embedded within its halo are thousands of globular clusters, spherical collections of ancient stars that orbit the galaxy like swarms of bees around a hive. These clusters number in the thousands, far more than the Milky Way's relatively modest population, and serve as relics of the galaxy's rich and violent formation history. Each globular cluster in M87 is a time capsule, containing stars among the oldest in the universe, formed in the early epochs of cosmic history. Studying them provides clues about the conditions that prevailed when galaxies first began assembling. Their motions and distributions also offer vital information about the dark matter halo that enshrouds M87, an invisible yet dominant component that governs the galaxy's overall gravitational field. The immense mass of M87 not only influences its own structure, but also plays a dominant role within the Virgo cluster. As one of the cluster's central galaxies, M87 acts as a gravitational anchor, affecting the motions of nearby galaxies and the distribution of hot gas that fills the spaces between them. X-ray observations from observatories like Chandra have shown that this gas is not distributed evenly but is instead shaped by the energetic feedback from M87's central engine. Cavities, ripples, and shock fronts in the gas testify to the ongoing interplay between the galaxy's active nucleus and its larger cosmic environment. Even today, M87 continues to evolve, albeit on timescales far longer than human comprehension. It remains a dynamic participant in the cosmic ballet, growing through the slow accretion of smaller galaxies and clusters, its black hole feeding intermittently on infalling matter, occasionally lighting up the galaxy in bursts of energy visible across the universe. To study M87 is to study the life cycle of galaxies themselves, from their chaotic beginnings to their majestic, mature forms. Yet, for all that we have learned about Messier 87, countless mysteries remain. How exactly are its jets launched and sustained across such enormous distances? What governs the feeding cycles of its central black hole? How does the galaxy's activity shape the evolution of the Virgo cluster as a whole? Each observation uncovers new layers of complexity, reminding us that the universe always holds more secrets than answers. Peering into the heart of M87, we are not merely observing a distant galaxy. We are glimpsing the profound forces that have shaped the cosmos from its earliest moments. The study of M87 connects us to the origins of structure in the universe, to the behavior of matter under extreme conditions, and to the ultimate fate of galaxies across cosmic time. Scientists could now study black holes not only through their indirect effects on nearby matter, but by directly observing the region surrounding the event horizon itself. The implications of this breakthrough were profound, offering a rare glimpse into the dynamics of space-time at its most extreme and validating predictions that had remained untested since the early 20th century. The success of imaging M87's black hole also sparked new questions, igniting fresh debates about the nature of black holes, the behavior of matter under extreme gravitational forces, and the future possibilities of imaging even more elusive cosmic phenomena. Messier 87's black hole, however, is not just an isolated feature sitting passively at the galaxy's center. It exerts a tremendous influence on its environment, most notably through the enormous relativistic jet that it ejects from its core. This jet is composed of highly energetic particles accelerated to speeds close to that of light, spewing forth across intergalactic space for nearly 5,000 light-years. Observed across many wavelengths, from radio to visible light to X-rays, the jet of M87 stands as one of the most prominent and extensively studied features in the entire universe. The origin of this jet lies in the twisted, powerful magnetic fields generated by the accretion disk of superheated matter swirling around the black hole. As the black hole feeds, it simultaneously launches these colossal jets perpendicular to the disk's plane, channeling energy outward in narrow beams that can extend for thousands, even millions, of light years. In the case of M87, the jet's incredible size makes it visible even in amateur telescopes under good conditions, a testament to the ferocity and scale of the processes at play. Researchers studying M87's jet have gleaned invaluable insights into the workings of active galactic nuclei, AGN, those mysterious regions at the centers of certain galaxies where supermassive black holes dominate their surroundings through emissions of staggering energy. In fact, M87 is classified as a radio galaxy, a type of AGN that emits strong radio waves thanks to these energetic jets. By analyzing the structure, composition, and motion of the jet, astronomers have tested fundamental theories about relativity, magnetohydrodynamics, and high-energy astrophysics. Beyond the black hole and its jet, the broader structure of M87 reveals layers of complexity that continue to challenge our understanding of galaxy formation and evolution. Its vast halo of stars is not randomly distributed but shows subtle patterns hinting at a turbulent history of galactic mergers and interactions. M87's position at the center of the Virgo cluster suggests it has cannibalized numerous smaller galaxies over billions of years, growing larger and more massive with each cosmic meal. Evidence of these past mergers is seen in the shells, ripples, and streams of stars observed in its outer halo, remnants of once independent galaxies now subsumed into M87's colossal gravitational grasp. Adding further depth to M87's intricate portrait are its globular clusters, dense, spherical collections of ancient stars that orbit the galaxy in a vast swarm. M87 possesses an astonishing number of these clusters, estimated to be in the range of 12,000 to 15,000, far exceeding the Milky Way's relatively modest population of about 150. These globular clusters serve as fossil records, preserving information about the earliest epochs of galactic assembly, offering a unique window into the processes that shaped not only M87 but the cosmos at large. The galaxy's immense mass, including its dark matter halo, ordinary matter, and central black hole, exerts a profound gravitational influence on its surroundings. As a dominant member of the Virgo cluster, M87 plays a central role in the dynamics of this cosmic neighborhood, affecting the motions of nearby galaxies and contributing to the overall gravitational binding of the cluster. Observations of M87 and its environment have helped astronomers map the distribution of dark matter within the cluster, advancing our understanding of one of the universe's greatest mysteries. Moreover, M87 serves as a laboratory for studying phenomena that stretch the limits of human comprehension. The interactions between its black hole, jet, stellar halo, and surrounding intergalactic medium provide a living canvas on which the fundamental forces of nature, gravity, electromagnetism, and quantum mechanics, perform a complex, interwoven ballet. By probing M87 across multiple wavelengths, scientists can piece together a multidimensional view of how matter and energy behave under the most extreme conditions known to exist. The story of M87 is also a story of time. The light we see today left the galaxy some 53 million years ago, at a time when the early ancestors of whales were just beginning to venture into the seas of prehistoric Earth. It is a humbling realization that as we gaze upon this distant giant, we are witnessing a scene from a past so remote that it predates the emergence of most modern forms of life. In this sense, M87 stands as a bridge between epochs, linking the deep past with our present understanding and reminding us of the staggering scales involved in cosmic observation. Even the individual stars of M87 tell tales of ancient epochs. Many of its stars are old, formed during the galaxy's earliest periods of intense star formation. Their chemical compositions, ages, and motions offer clues about the galaxy's formation history, the rates of star birth and death, and the processes that enrich the cosmos with heavier elements necessary for the creation of planets and life. By studying the spectra of these stars, astronomers can reconstruct the sequence of events that led to the formation of M87's present-day structure. M87's role as an archetype of giant elliptical galaxies extends beyond mere classification. It serves as a keystone in cosmological models. Understanding how such galaxies form, grow, and evolve is critical for piecing together the larger puzzle of cosmic history. Theories of hierarchical galaxy formation, where small structures merge to form larger ones, find a natural testing ground in galaxies like M87. Its enormous size, mass, and complex structure embody the cumulative effects of billions of years of cosmic evolution. In the broader context of the universe's history, M87 offers insights into the behavior of matter and energy at both galactic and intergalactic scales. The interactions between its hot gas halo and the surrounding intracluster medium reveal the dynamics of galaxy clusters, shedding light on processes such as ram pressure stripping, galactic cannibalism, and the heating and cooling cycles that govern large-scale structures. The hot gas permeating the Virgo cluster, detectable through X-ray observations, interacts with M87's own extended atmosphere. This interaction creates complex structures such as shock fronts, bubbles, and cavities, carved out by the mechanical energy injected by the supermassive black hole's activity. These features provide direct evidence of feedback processes, whereby black holes influence their host galaxies and even entire clusters by regulating star formation and redistributing energy and matter across vast distances. The feedback mechanisms observed in M87 are critical to solving one of the long-standing problems in cosmology: why galaxies like M87 cease forming new stars despite having ample supplies of gas. The jets and outflows powered by the central black hole heat the surrounding gas, preventing it from cooling and collapsing into new stars, effectively quenching further star formation. This self-regulating mechanism underscores the pivotal role that black holes play in shaping the life cycle of galaxies. Thus, M87 is not merely an isolated curiosity in the night sky. It is a microcosm of the universe's grandest themes: creation and destruction, order and chaos, light and darkness. It embodies the intricate interplay between matter and energy, the relentless march of time, and the ceaseless quest of humanity to understand the cosmos. In addition to its sheer visibility and power, the jet of M87 plays a critical role in the evolution of the galaxy and its surrounding environment. As the relativistic jet shoots outward, it injects vast amounts of energy into the intergalactic medium, heating surrounding gas and preventing it from cooling and collapsing to form new stars. This process, known as feedback, is essential for regulating galaxy growth, and in the case of M87, it has helped maintain the galaxy's immense, yet relatively stable, structure over billions of years. Furthermore, the jet is a laboratory for high-energy physics on scales impossible to replicate on Earth. The particles within the jet are accelerated to energies that challenge our understanding of physics, providing clues to the behavior of matter under the influence of intense gravitational and magnetic fields. Observations of the jet across multiple wavelengths have revealed complex structures, including shock waves, knots of compressed material, and signs of turbulence, all offering rich data for astronomers and physicists to unravel. Beyond the jet, Messier 87 itself is a marvel of galactic evolution and cosmic architecture. As a giant elliptical galaxy, it occupies a dominant position within the Virgo cluster, the nearest large cluster of galaxies to our local group. M87 is not merely one galaxy among many. It is a central anchor, a gravitational titan that exerts influence over numerous neighboring galaxies. Its mass extends far beyond what is visible, with a vast halo of hot gas detectable in X-rays and a massive dark matter component that outweighs its luminous matter by a significant margin. The structure of M87 is characterized by its smooth, featureless light profile, a stark contrast to the intricate arms and dust lanes seen in spiral galaxies. Its stars are predominantly old, with low levels of new star formation occurring within its boundaries. This aging stellar population gives M87 a yellowish hue when observed in visible light, a testament to its maturity and the long history of star formation that occurred early in its lifetime. Adding to its richness, M87 hosts an extraordinary number of globular clusters, dense, spherical collections of ancient stars orbiting the galaxy's core. Estimates suggest that M87 possesses more than 12,000 globular clusters, far exceeding the few hundred found around the Milky Way. These clusters provide invaluable insights into the early epochs of galaxy formation, acting as fossil records of the conditions present during the universe's youth. Studying M87's globular clusters has revealed that they possess a wide range of metallicities, suggesting that the galaxy underwent multiple major mergers throughout its history. Each merger likely contributed new stars, new clusters, and new layers of complexity to the galaxy's vast structure. The dynamics of these globular clusters also serve as independent evidence for the existence of the supermassive black hole, as their motions are influenced by the enormous gravitational well at the galaxy's heart. Moreover, Messier 87's interaction with the Virgo cluster is a story of cosmic competition and cooperation. While gravitationally binding smaller galaxies, M87 itself moves through the cluster's dark matter and intracluster medium, producing ripples and shocks that are detectable in X-ray wavelengths. The galaxy's motion and the feedback from its central black hole shape the evolution of the cluster as a whole, influencing the distribution of gas, the cooling rates of the medium, and the growth of other galaxies within the cluster. Beyond its physical characteristics, M87 holds a special place in the history of astronomical research. It has been a favorite target for radio astronomers since the early days of the field, due to the strength of its jet and the unique properties of its core. Early radio maps of M87 revealed lobes of emission extending far beyond the optical boundaries of the galaxy, structures that hinted at the powerful processes occurring at its center long before the black hole was directly imaged. Infrared observations have also unveiled layers of dust and cooler material within M87, offering a more nuanced picture of the galaxy's internal environment. While M87 lacks the rich, star-forming regions seen in spirals, it is not entirely devoid of dust and gas, and these components play subtle but important roles in the galaxy's ongoing evolution. Even the dark matter halo surrounding M87 is a subject of intense study. Through techniques such as gravitational lensing, where the galaxy's mass bends the light of background objects, astronomers have been able to map the distribution of invisible matter in and around M87. These studies contribute to the broader understanding of dark matter's role in shaping the cosmos, providing crucial data points for testing and refining cosmological models. M87's sheer mass and size also make it a key player in gravitational wave astronomy. Future detections of gravitational waves from supermassive black hole mergers within galaxy clusters like Virgo could be influenced by the presence of a giant like M87. Understanding its dynamics and mass distribution is essential for predicting and interpreting the subtle signals that observatories like LISA, the Laser Interferometer Space Antenna, hope to capture in the coming decades. Culturally, Messier 87 has transcended the boundaries of the scientific community, capturing public imagination in a way few astronomical objects ever have. The release of the first image of its black hole sparked a wave of artistic interpretations, philosophical reflections, and even memes, demonstrating the profound impact that a single astronomical achievement can have on society at large. It reminded humanity of its boundless curiosity, its relentless drive to peer into the unknown, and its capacity to achieve the seemingly impossible through collaboration and ingenuity. As technology continues to advance, the future promises even deeper insights into M87. Next-generation telescopes, both ground-based and spaceborne, will probe the galaxy's innermost regions with unprecedented resolution. Instruments like the James Webb Space Telescope and the upcoming Extremely Large Telescope, ELT, are poised to reveal new layers of complexity, from the behavior of matter at the edge of the event horizon to the faint whispers of ancient stars hidden within the galaxy's vast expanse. Continued observations of the jet will also enhance understanding of the physics of relativistic outflows, potentially answering questions about the role of magnetic fields, the mechanisms of particle acceleration, and the interactions between jets and their surrounding environments. These studies have implications that extend far beyond M87 itself, touching on the behavior of active galactic nuclei throughout the cosmos and offering analogies to processes that occur on smaller scales around stellar mass black holes. Perhaps most intriguingly, M87 serves as a beacon for the study of cosmic evolution on grand scales. By examining its properties, scientists can piece together the history of galaxy formation and growth from the early universe to the present day. M87 embodies the story of cosmic maturity, a tale of mergers, accretion, feedback, and the slow sculpting of matter into the grand structures that populate the universe. The black hole at M87's core, now immortalized by the Event Horizon Telescope, stands as both a literal and metaphorical gateway. It represents the frontier of human knowledge, a reminder that beyond the familiar lies a realm governed by forces we are only beginning to understand. Every photon captured, every data point analyzed, and every theory tested against the realities of M87 brings humanity one step closer to comprehending the full tapestry of the cosmos. This process of galactic mergers has given M87 a distinctive appearance compared to more orderly spiral galaxies like the Milky Way, resulting in a massive, featureless, elliptical shape that stretches across hundreds of thousands of light-years. Unlike spiral galaxies that exhibit detailed structures such as arms and dust lanes, M87 possesses a more uniform glow, with its stars distributed in a roughly spherical or ellipsoidal form, creating an image of serene grandeur masking the turbulent, violent processes that shaped it. Embedded within this sprawling galactic halo is an extraordinary population of globular clusters, dense, spherical collections of hundreds of thousands of stars bound together by gravity. M87 is home to over 12,000 globular clusters, far exceeding the few hundred found around the Milky Way. These clusters orbit the galaxy in extended halos, forming a glittering swarm that extends far beyond the central regions. Studying these globular clusters provides astronomers with vital clues about the formation history of M87, as their ages, chemical compositions, and motions carry the fingerprints of ancient events, such as mergers and accretion episodes that occurred in the galaxy's distant past. Moreover, the vast reservoir of hot, X-ray emitting gas that envelopes M87 speaks to its role as a powerhouse within the Virgo cluster. This hot gas, observed using space-based telescopes such as Chandra, acts as an archive of cosmic history, recording the energy inputs from supernovae, galactic collisions, and the ever-present influence of M87's active galactic nucleus. Intricate patterns within this gas, such as bubbles and ripples, reveal the footprint of the black hole's activity over millions of years, with outbursts from the core inflating cavities in the surrounding medium, much like cosmic sound waves echoing through intergalactic space. As if these attributes were not enough to solidify M87's reputation as one of the universe's grandest natural wonders, the galaxy's central black hole continues to serve as an object of immense fascination and ongoing study. Future observations, particularly those from enhanced versions of the Event Horizon Telescope, promise to unveil even finer details of the black hole's shadow, the dynamics of the accretion disk, and the magnetic structures that give rise to the magnificent jet. Scientists hope to measure the spin of the black hole more precisely, map the environment closer to the event horizon, and perhaps even witness changes in the appearance of the shadow over time, offering real-time glimpses into one of the most extreme environments known to physics. In addition to direct imaging, gravitational wave astronomy offers a complementary method of studying M87's central black hole. Although no mergers have yet been detected from such supermassive black holes, future gravitational wave observatories like LISA, Laser Interferometer Space Antenna, might one day catch the ripples produced by the coalescence of supermassive black holes within massive galaxies like M87. Such a discovery would not only confirm existing theories but would also illuminate the hidden narratives of cosmic evolution on colossal scales. Through all these layers, its immense size, ancient globular clusters, colossal jet, and supermassive black hole, Messier 87 stands as a symbol of cosmic grandeur and complexity. It reminds us that galaxies are not static collections of stars, but dynamic, evolving ecosystems shaped by the interplay of gravity, matter, and time itself. Every photon we capture from M87, every particle we detect from its jet, and every vibration we sense through gravitational waves adds to our portrait of a living universe, vast beyond comprehension yet intricately connected through the fundamental forces that govern existence. In the deepest sense, M87 challenges us to think bigger, to stretch our imaginations beyond the familiar confines of our solar system and Milky Way. It urges us to ponder questions that have no easy answers. How did the first black holes form? What is the ultimate fate of galaxies like M87? Could civilizations ever arise and endure near such a powerful nucleus? Or is it a realm forever hostile to life? What secrets remain hidden within the shadows of its immense core, and what new technologies will be needed to uncover them? Each new observation of Messier 87 serves as both an achievement and an invitation, an achievement in expanding human knowledge, and an invitation to continue exploring the vast, mysterious cosmos that has given rise to wonders like M87, to us, and to the endless future discoveries that await. These interactions were not gentle. They were cataclysmic events, with gravitational forces ripping stars from their original galaxies and flinging them into new orbits within M87's expanding halo, while streams of gas were either absorbed or dispersed into the vast intergalactic medium. Over billions of years, these processes gradually smoothed out the scars of collision, leaving behind the immense and seemingly calm elliptical galaxy we observe today. Yet beneath this outward tranquility, M87 retains the memory of its turbulent past, encoded in the motions of its stars and the distribution of its dark matter. Dark matter, though invisible, exerts a profound influence on the structure and dynamics of M87. Observations of the velocities of stars and globular clusters, along with gravitational lensing effects, reveal that a substantial portion of M87's mass is made up of this mysterious, unseen component. The presence of dark matter explains the galaxy's immense gravitational pull, which binds its stars and clusters over such vast distances, and it plays a crucial role in maintaining the galaxy's stability over cosmic timescales. Despite its vast mass and size, M87 is not an isolated island in space. It sits at the heart of the Virgo cluster, a gravitationally bound collection of over 2,000 galaxies, and its influence extends across the entire cluster. Through its massive gravitational field, M87 helps shape the motions of neighboring galaxies, drawing them into complex orbits and interactions that slowly but surely alter the fabric of the cluster itself. Intracluster gas, heated to millions of degrees, fills the space between these galaxies, emitting X-rays detectable by space-based observatories, and much of this gas is influenced by the activity of M87's central black hole and jet. At larger scales, M87 becomes part of even grander cosmic structures. The Virgo cluster, in which M87 resides, is itself part of the Laniakea supercluster, a massive web of galaxies and clusters bound together by gravity over distances spanning hundreds of millions of light-years. Within this cosmic web, M87 stands as a titan among titans, a colossal structure whose history, dynamics, and ongoing evolution offer insights not only into the nature of individual galaxies but into the architecture of the universe itself. Studying M87 provides astronomers with a window into nearly every important aspect of galactic and cosmic evolution: the growth of supermassive black holes, the formation of jets and active galactic nuclei, the dynamics of galaxy mergers, the role of dark matter, the physics of relativistic particles, the heating of intracluster gas, and the large-scale structure of the universe. Each observation of M87 adds another piece to the cosmic puzzle, helping to refine models of how galaxies form and evolve from the primordial gas of the early universe to the majestic, complex systems we see today. Moreover, the continued monitoring of M87's black hole by projects like the Event Horizon Telescope promises even more discoveries in the near future. By observing changes in the accretion disk and jet structure over time, scientists hope to understand the life cycles of black holes, the mechanisms that produce powerful jets, and the fundamental behavior of gravity under the most extreme conditions known to science. In a sense, M87 is both a relic and a beacon. It carries within its vast expanse the memory of the universe's violent youth, and it projects outward through its jet a message of ongoing activity and transformation. The galaxy's quiet glow belies a dynamic history of creation and destruction, of collision and fusion, of light and darkness playing out on unimaginable scales. Every photon that reaches our telescopes from M87 has traveled millions of years to tell us this story, a narrative written across the fabric of space and time itself. This story continues to unfold, as each new observation peels back another layer of mystery, challenging our understanding and inspiring ever deeper questions. Why did M87's black hole grow so massive? What precise mechanisms control the launching of its jet? How does the galaxy's dark matter halo interact with its luminous components? How will M87 continue to evolve in the future, as the Virgo cluster itself changes over billions more years? These questions are not merely academic. They cut to the heart of our quest to understand the universe and our place within it. In contemplating Messier 87, we are reminded of the grandeur and complexity of the cosmos, of forces and timescales so vast they defy everyday comprehension, yet which are intimately connected to the fundamental workings of reality. Through the light of M87, through the gravity of its black hole, through the jets that span the void, we glimpse the universe not as a static backdrop but as a living, evolving entity, rich with drama and meaning. And so, the journey into understanding Messier 87 continues, an endless voyage across space and time, fueled by curiosity, wonder, and the unyielding human desire to know the universe from which we came. The environment of the Virgo cluster is not a calm one. Galaxies within the cluster are constantly moving, interacting, and sometimes colliding with one another, creating a chaotic cosmic dance that continually reshapes the structure of the cluster over time. As one of the central giants in the cluster, M87 plays a key role in these interactions. Its enormous mass and gravitational pull not only affect the dynamics of other galaxies but also influence the behavior of the hot, diffuse gas that fills the space between the galaxies, known as the intracluster medium. The intracluster medium in the Virgo cluster is a vast, nearly invisible sea of ionized gas that is heated to millions of degrees by the ongoing activity of the cluster's galaxies, including M87. This gas emits X-rays, which astronomers have detected using powerful space telescopes such as Chandra. The interaction between M87 and the intracluster medium is profound. M87's central black hole, with its voracious appetite for surrounding matter, exerts a considerable impact on the gas. Jets of relativistic particles from the black hole inject energy into the medium, creating bubbles and ripples that act as a kind of cosmic feedback mechanism, affecting the evolution of both M87 itself and the cluster as a whole. Through these feedback processes, M87 influences the overall temperature and density of the intracluster gas. The energy deposited by the galaxy's active nucleus prevents the gas from cooling too rapidly, which could otherwise lead to star formation within the cluster. This feedback loop is part of a delicate balance that controls the star formation rates within galaxies like M87 and others in the cluster. In the case of M87, the continuous inflow of material into its central black hole and the resulting energy release through its jet may have contributed to the suppression of star formation in the surrounding regions, making M87 an example of an aging galaxy, where star formation has slowed down significantly. The intricate relationship between M87 and the larger Virgo cluster is also reflected in the movement of other galaxies. M87's immense gravitational field not only draws galaxies towards it but also helps maintain the overall structural integrity of the cluster. Over time, smaller galaxies may be drawn into M87, adding to its mass and altering its internal structure. The motions of these galaxies, along with the dynamics of the gas, create a complex web of interactions that shape the future of the cluster. These processes, occurring over billions of years, will continue to mold the galaxies and the intracluster medium, guiding their evolution toward an uncertain future. In addition to these larger cosmic forces, M87 also reveals a history of internal transformation and change. The galaxy's supermassive black hole, which resides at its core, serves as a record of the galaxy's growth and evolution. Black holes of this size are believed to form through the merger of smaller black holes, as well as the accumulation of matter from the surrounding galaxy. In the case of M87, the growth of its black hole has likely been influenced by the galaxy's history of mergers and accretions, events that have shaped the distribution of stars, gas, and dark matter throughout the galaxy. The presence of the black hole also links M87 to the broader theme of active galactic nuclei, AGN, regions at the centers of galaxies where supermassive black holes are actively accreting material and emitting enormous amounts of energy. M87's AGN, though not as visibly active as some other AGN, still exhibits powerful outflows in the form of its relativistic jet. This jet, composed of particles traveling at nearly the speed of light, extends for thousands of light-years into intergalactic space, and it serves as a reminder of the extreme forces at play within the galaxy. The study of M87's jet provides valuable insight into the mechanisms behind the acceleration of particles to such high velocities and into the broader processes of energy release and matter transport within the central regions of galaxies. As astronomers continue to observe M87, new insights into the nature of black holes and their role in the evolution of galaxies are likely to emerge. The Event Horizon Telescope, which provided the first-ever image of a black hole's event horizon in 2019, has already turned its attention to M87's supermassive black hole. The image captured by the telescope revealed a bright ring of light surrounding the black hole's shadow, marking a groundbreaking achievement in the study of black holes. This observation has opened up new avenues for exploring the properties of black holes, including their spin, mass, and the structure of their accretion disks. Future observations, using both the Event Horizon Telescope and other advanced instruments, will further deepen our understanding of these enigmatic objects and their influence on the surrounding environment. The discovery of the black hole in M87 has also spurred broader questions about the formation and growth of supermassive black holes in the early universe. How did such massive objects form in the first place, and what role did they play in the development of galaxies? Some theories suggest that the first black holes formed through the collapse of primordial gas clouds, while others propose that they grew through the merger of smaller black holes over time. The study of M87's black hole offers a unique opportunity to probe these early stages of black hole formation and to understand the processes that led to the creation of the supermassive black holes we observe today. The mysteries surrounding M87 are not limited to its black hole alone. The galaxy's rich history of mergers and interactions provides clues about the broader processes of galaxy formation and evolution. It is believed that galaxies like M87, which are classified as giant ellipticals, form through the accumulation of smaller galaxies over time. These mergers often result in the redistribution of stars, gas, and dark matter, leading to the formation of a more massive and compact galaxy. The study of M87's structure, including the distribution of its globular clusters and the motion of its stars, helps to illuminate the processes that drive the growth of such galaxies. One of the key questions that remains unanswered is the role of dark matter in the formation and evolution of galaxies like M87. Dark matter, which makes up a significant portion of the galaxy's mass, is thought to be responsible for the galaxy's gravitational pull, yet it cannot be observed directly. Its presence is inferred through the gravitational effects it has on visible matter, such as stars and gas. In M87, the distribution of dark matter plays a crucial role in shaping the galaxy's overall structure and in maintaining its stability. Understanding how dark matter interacts with other components of the galaxy, including the stars and the black hole, is essential for developing a complete picture of the galaxy's formation and evolution. As the study of Messier 87 progresses, it continues to offer invaluable insights into the workings of the universe. From its massive black hole to its interactions with the Virgo cluster, M87 serves as a laboratory for understanding the fundamental processes that govern the cosmos. The galaxy's intricate web of stars, gas, and dark matter provides a snapshot of the complex dynamics that shape galaxies, while its central black hole offers a window into the extreme conditions that govern the behavior of matter and energy in the universe's most hostile environments. Through continued observation and analysis, astronomers will continue to unravel the mysteries of M87, one of the universe's most intriguing and enigmatic objects. As we delve deeper into the mysteries of M87, it becomes apparent that the galaxy's significance reaches beyond its size and the intriguing phenomena observed within it. One of the most captivating aspects of M87 is its role in the broader understanding of galactic evolution and cosmic feedback loops. The interaction between the supermassive black hole at M87's core and the galaxy's surrounding environment helps to shed light on the broader processes that govern the evolution of galaxies, not just in the local universe, but in the universe as a whole. The active nucleus of M87, where the supermassive black hole resides, is a site of incredibly dynamic activity. The black hole itself acts as a cosmic engine, constantly feeding off material from the surrounding accretion disk. This disk is composed of gas, dust, and other debris that spirals inward toward the black hole. As this material falls toward the event horizon, it is heated to extreme temperatures, causing it to emit vast amounts of radiation across the electromagnetic spectrum. This radiation, in turn, drives powerful outflows that can influence the surrounding gas and stars. These outflows, known as jets, are among the most striking features of M87, extending for thousands of light years and carrying enormous amounts of energy into the intergalactic medium. These jets are not merely a fascinating spectacle. They serve as an important tool for understanding the physics of black holes and their influence on their host galaxies. The study of M87's jets has revealed valuable information about the acceleration of particles to relativistic speeds, as well as the mechanisms behind the transfer of energy from the black hole to the surrounding environment. The processes that govern these jets are still not entirely understood, but they represent a key area of active research in astrophysics. Moreover, the jets observed in M87 play a critical role in regulating the growth and evolution of the galaxy itself. The energy and momentum carried by these jets can act as a form of feedback that prevents excessive cooling of the gas in the galaxy's core. If the gas were to cool too rapidly, it could collapse and form new stars, potentially leading to an unsustainable rate of star formation. However, the feedback provided by the jets of M87 helps to maintain a balance, preventing star formation from becoming too rampant, while also ensuring that the galaxy's gas remains in a stable state. This delicate balance between heating and cooling is a crucial aspect of galactic evolution, and it can have far-reaching implications for our understanding of the life cycle of galaxies. In this regard, M87 serves as a powerful example of how black holes and their feedback mechanisms can shape the destiny of an entire galaxy. The active nucleus of M87 is not just a byproduct of the galaxy's evolution, but a central driver of its ongoing transformation. The influence of the black hole on the surrounding gas, stars, and dark matter creates a complex interplay that shapes the overall structure and evolution of M87. As astronomers continue to study these interactions, they are uncovering new insights into the role of supermassive black holes in the formation, growth, and eventual demise of galaxies. The study of M87 is also revealing important clues about the nature of the very largest structures in the universe. While individual galaxies like M87 are fascinating in their own right, they are also part of much larger cosmic structures, such as galaxy clusters and superclusters. The Virgo cluster, where M87 resides, is one of the most well-studied galaxy clusters in the universe, and it provides a unique opportunity to explore the dynamics of galaxies within these massive cosmic systems. The Virgo cluster itself is a dense collection of galaxies, stars, gas, and dark matter, all bound together by gravity. As the largest galaxy in the cluster, M87 plays a dominant role in shaping the dynamics of its neighbors. The gravitational influence of M87 affects the orbits of smaller galaxies, sometimes causing them to spiral inward toward the central giant. These interactions can result in galaxy mergers, where smaller galaxies are absorbed into M87 or other large galaxies within the cluster. Over time, these mergers can lead to the growth of M87, increasing its mass and changing its internal structure. The Virgo cluster is not a static system, however. It is a dynamic environment, with galaxies constantly moving and interacting. These interactions can lead to the stripping of gas from galaxies, as the hot intracluster medium exerts pressure on the gas within individual galaxies. This phenomenon, known as ram pressure stripping, has been observed in the Virgo cluster, and it is thought to play a key role in the evolution of galaxies within clusters. M87, with its immense gravitational pull, is likely to be involved in these processes, both directly and indirectly. As galaxies interact within the Virgo cluster, they contribute to the overall growth and evolution of the cluster. The interactions between galaxies, along with the feedback provided by active galactic nuclei like M87, play a crucial role in regulating star formation, gas distribution, and the overall dynamics of the cluster. The study of M87 and its place within the Virgo cluster is providing astronomers with a unique window into the processes that drive the formation and evolution of galaxy clusters, helping to illuminate the complex web of interactions that govern the large-scale structure of the universe. In addition to its role in shaping the dynamics of the Virgo cluster, M87 also provides valuable insight into the nature of dark matter, one of the most mysterious components of the universe. Dark matter, which makes up the majority of the mass in the universe, cannot be observed directly, but its presence is inferred through its gravitational effects on visible matter. In M87, dark matter plays a crucial role in maintaining the galaxy's stability. It is believed to be distributed in a massive halo around the galaxy, providing the gravitational support needed to hold the galaxy together. The study of dark matter in M87 and other galaxies is a key area of research in modern astrophysics. By examining the motion of stars and gas within M87, as well as the distribution of dark matter around the galaxy, astronomers can gain insights into the properties of this elusive substance. Some theories suggest that dark matter is made up of exotic particles that interact weakly with ordinary matter, while others propose that it consists of primordial black holes or other yet undiscovered objects. The ongoing study of M87 and its dark matter halo is helping to refine our understanding of dark matter and its role in the formation and evolution of galaxies. As we continue to explore the mysteries of M87, we are also gaining a deeper understanding of the processes that govern the life cycles of galaxies. From the formation of stars to the behavior of supermassive black holes, M87 serves as a cosmic laboratory, providing clues about the fundamental forces that shape the universe. The galaxy's interactions with the Virgo cluster, its black hole feedback mechanisms, and its role in the evolution of dark matter all contribute to our broader understanding of the cosmos. In the years to come, as new telescopes and observational techniques are developed, M87 will undoubtedly continue to be a focal point of scientific inquiry. With the potential for groundbreaking discoveries about the nature of black holes, dark matter, and galactic evolution, M87 stands as one of the most important objects in the sky. Its complexity and richness make it a subject of fascination for astronomers and astrophysicists alike, and its story is far from over. As we peer deeper into its core and unravel its many mysteries, we will undoubtedly uncover new insights into the workings of the universe and our place within it. M87, as one of the most extensively studied galaxies in the universe, continues to captivate scientists and astronomers alike with its extraordinary features. The unique qualities of M87 extend far beyond its sheer size and the powerful jets emanating from its supermassive black hole. In fact, one of the most intriguing aspects of M87 lies in its connection to some of the fundamental questions of cosmology. Questions that challenge our understanding of the very nature of space, time, and matter. The supermassive black hole at M87's center is not only a prominent player in the galaxy's dynamic behavior, but it also offers us an unparalleled opportunity to study the nature of black holes themselves. As black holes are invisible by their very nature, detecting and studying them is a tremendous challenge. However, through the study of their surrounding environments, such as the accretion disk, the relativistic jets, and the radiation they emit, scientists can infer the characteristics of these enigmatic objects. M87's black hole is particularly important in this regard because, being located in such a well-studied galaxy, it provides a detailed laboratory for understanding the physics of supermassive black holes. The Event Horizon Telescope, EHT, collaboration, a global network of radio telescopes, made a groundbreaking achievement in 2019 by capturing the first-ever image of a black hole. This image, which revealed the shadow of the supermassive black hole at the center of M87, was a landmark moment in astrophysics. The image showed a glowing ring of light surrounding a dark central region, which corresponded to the shadow of the black hole's event horizon. This achievement was not just a technological marvel but also a monumental scientific breakthrough, as it confirmed many of the theoretical predictions made by Einstein's general theory of relativity. The work done by the EHT in imaging M87's supermassive black hole was not only historic but also provided critical data that helped scientists understand the behavior of the black hole's environment. For instance, the precise measurements of the black hole's shadow allowed researchers to estimate the size of the event horizon and to test some of the key predictions of general relativity. One of the remarkable aspects of the EHT's findings was that the black hole's shadow appeared to be perfectly circular, consistent with the predictions of Einstein's theory. This confirmed that M87's black hole, despite its complex surroundings, behaves in ways that align with our understanding of the fundamental laws of physics. Beyond the immediate revelations about black holes, the image of M87's supermassive black hole also provides important clues about the formation and evolution of such objects. While supermassive black holes are thought to reside at the centers of most large galaxies, including our own Milky Way, the exact mechanisms behind their formation are still shrouded in mystery. Some theories suggest that supermassive black holes formed early in the universe's history, growing by accreting gas and merging with other black holes over time. Others propose that these objects might have formed through the collapse of massive clouds of gas, a process that could have taken place in the early universe. In the case of M87, the black hole's mass is estimated to be about 6.5 billion times that of the Sun, which places it firmly in the category of supermassive black holes. The formation of such a massive black hole in a relatively nearby galaxy, in cosmic terms, presents an opportunity to explore how these behemoths came to be. By studying the surrounding gas and stars, as well as the interactions between M87's black hole and its environment, scientists are gaining valuable insights into the complex processes that might have contributed to the growth and evolution of black holes over cosmic time. In addition to its role as a host for a supermassive black hole, M87 is also an important object for studying the larger-scale structure of the universe. As a member of the Virgo cluster, one of the most studied galaxy clusters, M87 provides a unique vantage point for understanding how galaxies interact within a cluster. Galaxy clusters are massive collections of galaxies, gas, and dark matter, all bound together by gravity. These environments are highly dynamic, with galaxies frequently interacting, merging, and colliding. The interactions within a galaxy cluster can have profound effects on the evolution of individual galaxies, as well as on the cluster as a whole. M87, being the largest and most massive galaxy in the Virgo cluster, is a dominant force within the cluster's gravitational potential. Its size and mass make it a key player in shaping the environment of the cluster. The gravitational influence of M87 has been shown to affect the motion of nearby galaxies, drawing them in and sometimes causing them to merge with the giant galaxy. This process of galaxy mergers is thought to be one of the key drivers of galactic evolution. When galaxies collide, their gas and dust are compressed, which can trigger new waves of star formation. However, the intense gravitational forces can also strip galaxies of their gas, which can inhibit further star formation. In the case of M87, this process of galaxy accretion has likely been ongoing for billions of years. As smaller galaxies are pulled into M87's gravitational well, they add to the mass and complexity of the galaxy, enriching it with new stars, gas, and other material. This dynamic environment also plays a role in the formation and evolution of the galaxy's central black hole. As smaller galaxies merge with M87, their gas can be funneled into the central black hole, fueling its growth and potentially increasing its energy output. The interaction between M87 and the rest of the Virgo cluster also provides important clues about the behavior of dark matter, the mysterious substance that makes up most of the mass in the universe. Dark matter cannot be observed directly, but its gravitational effects can be measured by studying the motion of galaxies and the distribution of mass within clusters. In the case of M87, the dark matter surrounding the galaxy provides crucial support for its structure. Without the presence of dark matter, M87 would not be able to hold together against the forces exerted by the galaxies and gas around it. The study of M87's dark matter halo has been a major focus of astrophysical research, as it provides one of the most detailed examples of how dark matter behaves on a galactic scale. By analyzing the motion of stars and gas in and around M87, astronomers have been able to map out the distribution of dark matter in the galaxy's outskirts. These observations are helping to refine our understanding of dark matter and its role in shaping the structure of galaxies and galaxy clusters. The results from M87 are also informing the ongoing search for dark matter particles, which are thought to interact only weakly with ordinary matter and could explain some of the galaxy's mysterious features. As we continue to study M87, both through ground-based telescopes and cutting-edge space observatories, we are also learning more about the broader forces that govern the universe. The supermassive black hole at M87's core, along with its dynamic accretion disk and relativistic jets, is a key laboratory for studying some of the most fundamental questions in physics. From the nature of black holes to the behavior of dark matter, M87 provides a rich and complex environment for exploring the fundamental forces that shape the universe. Looking forward, the future of M87 studies is full of exciting possibilities. New technologies, such as next-generation space telescopes and advanced computational models, will allow astronomers to probe deeper into the galaxy's core and to uncover even more secrets about its structure and behavior. As our understanding of M87 continues to evolve, we will no doubt gain new insights into the fundamental workings of the cosmos and our place within it. The study of M87, with its vast scale and its connections to the broader universe, remains one of the most important areas of research in modern astrophysics, and it is sure to yield many more groundbreaking discoveries in the years to come. The study of M87 is not only pivotal for understanding the galaxy itself but also provides insights into the cosmic processes that govern galaxy formation, evolution, and the dynamics of supermassive black holes. M87, as a central object in the Virgo cluster, acts as a crucial piece of the puzzle in piecing together the larger structure of the universe. Its long history of scientific observation and its rich datasets serve as a laboratory for testing ideas about galaxy clusters, the behavior of black holes, and the formation of large-scale cosmic structures. As astronomers continue to investigate M87, their findings could influence our understanding of the formation of other galaxies, especially those located at the center of galaxy clusters. While M87's size and mass make it a particularly interesting object, it is far from unique in terms of its place in the universe. There are many other massive galaxies located in clusters that share similar characteristics. The challenge for astronomers is to uncover whether M87 is representative of a broader class of galaxies, or whether its unique features make it an outlier. One of the critical aspects of M87's study is its role in understanding the formation of the supermassive black holes at the centers of galaxies. M87's black hole, with its mass of 6.5 billion times that of the Sun, provides us with a close look at how these objects evolve over cosmic time. The mass of such black holes and their effect on their host galaxies is a subject of great interest in astrophysical research. How do they grow to such immense sizes? What factors contribute to their immense gravitational pull, and what processes govern their accretion of matter? One possible mechanism that is under investigation is the growth of black holes through the merging of smaller black holes or the continuous accretion of gas and dust from their surrounding environment. The supermassive black hole in M87 is thought to have grown over billions of years, likely through the accretion of gas from its galaxy and possibly from smaller black holes that were once present in the cluster. This process of accretion involves the infall of matter into the black hole's gravitational well, creating a hot, dense accretion disk that radiates energy across the electromagnetic spectrum. The accretion disk around M87's black hole is an essential focus of study, as it provides valuable information about the physics of matter under extreme gravitational and energetic conditions. Additionally, the relativistic jets emerging from the black hole are a fascinating aspect of M87's behavior. These jets, composed of ionized gas and other particles, travel at nearly the speed of light and stretch for vast distances away from the galaxy's center. They offer a unique glimpse into the processes that occur near the event horizon of black holes. The exact mechanisms behind the formation and acceleration of these jets are still not fully understood, but they provide a direct connection between the black hole's central engine and the outer regions of the galaxy. Studying these jets helps astronomers explore how energy is transferred from the black hole to its surrounding environment, potentially influencing the evolution of the galaxy as a whole. The presence of these jets has far-reaching implications for our understanding of the role black holes play in shaping their galaxies. The energy and matter expelled by the jets can regulate the growth of stars in the galaxy by heating the surrounding gas and preventing it from cooling enough to form new stars. This feedback mechanism between the black hole and the galaxy's star formation is thought to be an essential part of the evolution of galaxies, particularly in the centers of clusters like the Virgo cluster. The study of these feedback processes is a critical area of research, as it has broad implications for understanding how galaxies evolve over cosmic time. Moreover, the jets also carry important clues about the physical properties of the black hole itself. The study of the polarization of light emitted by the jets, for example, can reveal information about the structure of the magnetic fields that play a key role in the jet's formation. These magnetic fields are thought to be crucial for channeling the gas and particles into narrow beams, which are then expelled from the black hole at relativistic speeds. Understanding the role of magnetic fields in the behavior of black holes could be an important step in understanding the fundamental physics of these exotic objects. In addition to their intrinsic scientific value, M87 and its supermassive black hole also provide an important test case for our broader understanding of cosmology and the laws of physics. The ability to study a black hole of M87's size and mass in such detail has enabled scientists to test some of the key predictions of general relativity. For instance, the fact that the black hole's shadow appears to be a perfect circle is consistent with predictions made by Einstein's theory of gravity. This is an important confirmation of our understanding of how black holes behave and how they interact with their environment. However, while general relativity has passed these tests, there are still many unanswered questions. For instance, scientists are still trying to understand the precise nature of the event horizon and what happens to matter that crosses it. Does it simply disappear, or is it somehow transformed in ways that are still beyond our comprehension? The study of M87's black hole, and others like it, may ultimately provide us with the answers to these questions and offer a deeper understanding of the true nature of spacetime. Furthermore, M87's position within the Virgo cluster allows researchers to explore the properties of galaxy clusters in general. As one of the largest galaxy clusters in the nearby universe, the Virgo cluster serves as a valuable observational laboratory for studying the interactions between galaxies, dark matter, and the intergalactic medium. The cluster's high galaxy density and the interactions between its galaxies provide a unique opportunity to study the effects of cluster environments on galaxy evolution. These interactions, such as galaxy mergers and the stripping of gas from smaller galaxies, can have a profound effect on the evolution of individual galaxies and contribute to the growth of central supermassive black holes like the one in M87. M87's central black hole is also one of the most studied examples of active galactic nuclei, AGN. AGNs are the energetic centers of galaxies, where a supermassive black hole is actively accreting matter and producing powerful radiation. The study of AGNs is crucial for understanding the role black holes play in the energy dynamics of galaxies and clusters. The radiation emitted by these black holes can have a significant impact on their host galaxies, affecting everything from star formation to the growth of the black hole itself. As one of the brightest and most active AGNs, M87 provides an invaluable window into the complex processes occurring at the heart of an active galaxy. In the years to come, advancements in observational technology will allow astronomers to gain even more detailed insights into M87. Upcoming telescopes and observatories, such as the James Webb Space Telescope and the next-generation Event Horizon Telescope, will push the boundaries of our ability to observe distant objects and study the universe's most extreme environments. These tools will allow scientists to continue unraveling the mysteries of M87's black hole, its jets, and its complex interactions with its surroundings. The study of M87 is far from over. As new technologies and methods emerge, there will be even more opportunities to deepen our understanding of this fascinating galaxy and its supermassive black hole. From the formation of galaxies and black holes to the fundamental laws of physics, M87 holds the potential to answer some of the most profound questions in science. As we continue to probe its depths, M87 will no doubt remain one of the most important and captivating objects in the universe, offering us a window into the heart of a galaxy and the mysteries of the cosmos itself. M87 stands as a monumental subject in the exploration of the universe, offering astronomers a critical case study of some of the most mysterious and extreme phenomena known to science. The wealth of data provided by this galaxy has shaped our understanding of cosmic processes, including the formation and behavior of supermassive black holes, galaxy clusters, and the intricate relationships between them. With each new discovery and every technological leap forward, our comprehension of M87 and the universe as a whole continues to evolve. A key aspect of M87's intrigue lies in its relationship with the Virgo cluster. The cluster, one of the most massive in the local universe, contains a diverse array of galaxies, ranging from small dwarf galaxies to massive ellipticals like M87. The interactions within this dense environment shape the galaxies that inhabit it, driving processes like galaxy mergers, star formation, and the redistribution of gas and dark matter. M87, as the dominant galaxy at the center of the cluster, is at the heart of these cosmic interactions, serving as both a product and an influence on the surrounding environment. The cluster's gravitational influence has profound effects on the dynamics of the galaxies within it. As galaxies move through the cluster, they experience tidal forces that can distort their shapes and strip away gas. These effects can hinder star formation in some galaxies while triggering it in others, contributing to the complex evolution of the cluster. M87, with its massive size and central position, plays a critical role in shaping the cluster's overall structure. It acts as the gravitational anchor of the Virgo cluster, influencing the motion of galaxies and the distribution of dark matter within the cluster. Dark matter, which makes up the majority of the mass in galaxy clusters, is another aspect of M87's cosmic environment that is critical to understanding the structure of the universe. While dark matter cannot be directly observed, its presence is inferred through its gravitational effects on visible matter. In the case of M87, dark matter is thought to be a significant factor in the formation and growth of its supermassive black hole. The distribution of dark matter within the Virgo cluster also affects the overall dynamics of the galaxies within it, including M87 itself. Understanding how dark matter interacts with galaxies like M87 is one of the ongoing challenges in cosmology, and M87's position at the center of the cluster makes it an essential object of study for researchers investigating this mysterious substance. The immense scale of M87 also highlights the vast distances that separate us from this galaxy. Located roughly 53 million light-years away from Earth, M87 is far enough that its study requires the most advanced observational tools available. The Event Horizon Telescope, for instance, relies on a network of radio telescopes spread across the globe to achieve the resolution needed to capture images of the black hole's event horizon. This technique, known as Very Long Baseline Interferometry, VLBI, enables astronomers to observe cosmic objects with a level of detail that would be impossible with a single telescope. The success of the Event Horizon Telescope's imaging of M87's black hole has opened the door for future observations of other supermassive black holes across the universe, providing a glimpse into the hidden workings of these enigmatic objects. The Event Horizon Telescope's success in capturing the first-ever image of a black hole's event horizon in 2019 was a landmark achievement in astrophysics. The image, known as the shadow of M87's supermassive black hole, provided a direct visual confirmation of the existence of black holes and offered a test of Einstein's general theory of relativity. This breakthrough is one of the most significant moments in modern science, as it provided an unprecedented view into the core of a black hole and offered new insights into the behavior of matter in the most extreme environments. The image of M87's black hole shadow was not just a visual accomplishment, but also a scientific milestone. It allowed researchers to test key predictions made by general relativity, such as the shape of the event horizon and the behavior of light near a black hole. The results of this observation were consistent with the predictions of general relativity, further solidifying Einstein's theory as the foundation of our understanding of gravity. This observation also provided valuable data on the properties of black holes, including their size, mass, and the behavior of matter in their immediate vicinity. In addition to its role in confirming general relativity, M87's supermassive black hole serves as a natural laboratory for testing other theories of gravity and physics. For example, scientists are using M87's black hole to investigate the nature of spacetime at the event horizon. The event horizon, the boundary beyond which nothing, not even light, can escape, is one of the most mysterious features of black holes. Theoretical physicists have long speculated about the nature of this boundary, and what happens to matter and information that crosses it. By studying M87's black hole, scientists hope to gain a deeper understanding of these fundamental questions, which may eventually lead to new breakthroughs in our understanding of the universe. Another intriguing aspect of M87 is its relativistic jets. These high-energy beams of particles shoot outward from the supermassive black hole at nearly the speed of light. The formation of these jets is still not fully understood, but they are believed to be a result of the interaction between the black hole's powerful magnetic fields and the infalling gas from the accretion disk. The jets can stretch for millions of light years, influencing the surrounding galaxy and even other galaxies in the cluster. These jets play a crucial role in regulating the amount of gas available for star formation, and their study can help us understand how black holes influence the evolution of galaxies. The energy output of these jets is enormous, and they can have a profound effect on the intergalactic medium. As the jets travel outward from the black hole, they inject energy into the surrounding gas, heating it to temperatures that prevent the formation of new stars. This feedback mechanism is an essential part of galaxy evolution, as it can help regulate the rate of star formation in the galaxy. The study of M87's jets, therefore, offers valuable insights into the processes that shape the evolution of galaxies and the role that supermassive black holes play in this process. M87's central black hole is not just a laboratory for testing theories of general relativity and galaxy evolution. It also provides an opportunity to explore some of the most profound questions in physics. The study of black holes challenges our understanding of spacetime, gravity, and the fundamental nature of the universe. The extreme conditions near a black hole, where gravity is so intense that it warps the fabric of spacetime itself, provide a unique environment for testing the limits of our current physical theories. The future of M87's study holds even more promise as new technologies emerge. The James Webb Space Telescope, set to launch in the near future, will provide new opportunities for observing distant galaxies and supermassive black holes. With its unprecedented sensitivity and resolution, the James Webb Space Telescope will allow scientists to study the galaxies and black holes at the center of galaxy clusters with greater detail than ever before. This will likely provide new insights into the formation and evolution of galaxies and black holes, as well as the relationship between them. Moreover, the continued development of gravitational wave astronomy holds the potential for even deeper insights into the nature of black holes. Gravitational wave detectors like LIGO and Virgo are already providing groundbreaking data on the mergers of stellar mass black holes. In the future, these detectors may be able to observe the mergers of supermassive black holes, such as those in galaxies like M87. These observations could provide new information on the formation and growth of supermassive black holes and offer additional tests of our understanding of gravity. M87 is more than just a distant galaxy. It is a cosmic laboratory that allows scientists to explore some of the most fundamental questions in astrophysics. Its supermassive black hole, relativistic jets, and position within the Virgo cluster make it an essential object of study for astronomers and physicists alike. As our technology advances and our understanding deepens, M87 will undoubtedly continue to play a key role in shaping the future of cosmology and astrophysics. The next decade promises to bring even more discoveries about M87 and other galaxies like it. With the continued advancement of observational technology, we will likely uncover new details about the processes that govern galaxy formation, black hole growth, and the evolution of large-scale structures in the universe. M87 will remain a cornerstone of these efforts, offering insights not only into the past and present of our universe but also into its future. M87's influence extends far beyond its immediate surroundings in the Virgo cluster. As a massive, well-studied galaxy, it has profound implications for understanding the broader cosmic structure. The immense gravitational pull of M87, together with its powerful black hole and relativistic jets, allows it to serve as a template for examining the processes that take place in other galaxies across the universe. While each galaxy is unique in its characteristics, the similarities in the way they evolve, grow, and interact with their surroundings make M87 a critical object in understanding galactic dynamics. Its location within the Virgo cluster provides an invaluable window into how galaxy clusters, as vast collections of galaxies bound by gravity, function. The Virgo cluster is an essential area of study not only because of its proximity but also due to the vast number of galaxies contained within it, making it a unique natural laboratory. M87, positioned at the center of this cluster, exerts significant gravitational influence over the surrounding galaxies, shaping their evolution. The intergalactic medium, which consists of hot, diffuse gas between galaxies, is a critical component of the study of galaxy clusters, as it holds many of the secrets to understanding the interactions between galaxies and the intergalactic space itself. M87's black hole has been a particular point of interest for astronomers. As one of the most massive black holes known, with a mass equivalent to billions of times that of the Sun, it challenges our understanding of how these cosmic giants form and evolve. While smaller black holes are formed from the collapse of individual stars, the origin of supermassive black holes like the one at the center of M87 remains an open question. There are several hypotheses about how such massive objects come into being, ranging from the accretion of large amounts of gas and dust over billions of years to the merging of smaller black holes in the early universe. Understanding the formation of supermassive black holes is one of the most pressing questions in modern astrophysics, and M87's black hole is at the heart of this inquiry. The black hole at the center of M87 is not only notable for its size but also for its interaction with its environment. The accretion disk surrounding it, composed of gas and dust falling into the black hole, is a hot, dense region where matter spirals inward, emitting enormous amounts of radiation in the process. This radiation can be observed by telescopes and provides valuable information about the conditions near the event horizon. The study of the accretion process helps astronomers understand the dynamics of material falling into black holes and the nature of the event horizon itself. The behavior of matter near the event horizon, particularly the way it is stretched and compressed by the intense gravitational forces, is a subject of much interest. In recent years, observations of M87's black hole have confirmed predictions made by general relativity, such as the bending of light near the black hole and the size and shape of the event horizon. These observations have helped solidify the theory of relativity as the most accurate model of gravitational behavior near black holes. However, there are still many mysteries to be unraveled, including the behavior of quantum particles at the event horizon and the potential for quantum effects to influence the formation of black holes. The relativistic jets emanating from M87's black hole add another layer of complexity to our understanding of these cosmic objects. These jets, composed of highly energized particles traveling at nearly the speed of light, are one of the most spectacular features of active galactic nuclei, AGN, like M87. The exact mechanism by which these jets are launched and accelerated to such extreme velocities remains unclear. However, it is generally believed that the black hole's powerful magnetic fields play a crucial role in directing and accelerating the particles. These jets can extend for millions of light years, carrying with them vast amounts of energy and impacting the surrounding galaxy and even the intergalactic medium. The interaction of these jets with the gas and dust surrounding the black hole can influence the rate of star formation in the galaxy, and play a key role in the evolution of the galaxy itself. The study of M87's jets has far-reaching implications for our understanding of galaxy evolution. The energy expelled by these jets can regulate the amount of gas available for star formation, essentially acting as a galactic thermostat. By heating the surrounding gas to temperatures that prevent it from cooling and condensing into new stars, the jets can suppress star formation. This feedback process is believed to be a crucial part of the evolutionary cycle of galaxies, helping to explain why some galaxies, like M87, have little to no ongoing star formation despite their massive size. Additionally, the relativistic jets provide insight into the magnetic fields that are thought to be responsible for launching and accelerating the jets. Magnetic fields play a fundamental role in the behavior of matter in and around black holes. The study of these fields, and the way they interact with the accretion disk and the surrounding material, is an area of intense research. As scientists continue to improve their ability to observe the fine details of black holes and their surroundings, they will likely gain a deeper understanding of the complex interplay between gravity, magnetism, and the behavior of matter in the extreme environments near black holes. The image of M87's black hole, captured by the Event Horizon Telescope in 2019, was not just a triumph for astrophysics. It was a visual confirmation of the theoretical predictions made by scientists for over a century. The black hole's shadow, or the event horizon, as seen in the image, is a direct observation of the region from which no light can escape, providing a unique glimpse into the workings of a supermassive black hole. The shadow was not simply a photographic representation. It was a significant achievement in the field of theoretical physics, testing the limits of general relativity and giving scientists an unprecedented opportunity to examine the most extreme environments in the universe. This achievement marked a significant turning point in our ability to study black holes. Previously, black holes were detected only through their effects on nearby matter, such as the gravitational pull they exert on nearby stars or the way they influence the movement of gas in an accretion disk. With the ability to observe the event horizon itself, scientists can now study the very boundary where our understanding of physics begins to break down. The capture of this image confirmed many of the predictions made by Einstein's theory of general relativity, such as the shape and size of the event horizon. However, it also raised new questions, particularly about the behavior of matter at the event horizon and the potential for quantum effects to play a role in the formation and growth of black holes. The image of M87's black hole was not just a scientific breakthrough, it was a technological marvel. The Event Horizon Telescope, a global network of radio telescopes, was able to capture this image by combining data from telescopes located all over the world. This collaborative effort, involving scientists and astronomers from institutions across the globe, highlights the importance of international cooperation in advancing our understanding of the universe. The success of the Event Horizon Telescope has set the stage for future observations of other supermassive black holes and has opened up new possibilities for studying the most extreme objects in the universe. Looking forward, the continued study of M87 and its supermassive black hole will provide further insights into the nature of black holes, galaxy evolution, and the role that supermassive black holes play in shaping the universe. The study of relativistic jets, the behavior of matter near the event horizon, and the role of magnetic fields will all continue to be central to our understanding of these enigmatic cosmic objects. M87's black hole, with its unique properties and its position at the center of a galaxy cluster, is likely to remain a focal point of research for years to come. In addition to the insights provided by the Event Horizon Telescope, other astronomical missions are also contributing to our understanding of M87. Observations from space-based telescopes, such as the Hubble Space Telescope and the Chandra X-ray Observatory, provide complementary data that help to paint a more complete picture of the galaxy and its supermassive black hole. These observations allow scientists to study M87 across different wavelengths of light, from visible to X-rays, providing a more detailed view of the processes at play in this distant galaxy. The study of M87 is not just about understanding one galaxy. It is about unraveling the mysteries of the universe itself. As we continue to study galaxies like M87, we gain insight into the fundamental processes that govern the formation, evolution, and interaction of galaxies and black holes. With each new discovery, we come closer to understanding the true nature of the cosmos and the forces that shape it. As we venture deeper into understanding Messier 87 and its monumental contributions to astrophysical research, it's important to remember that M87 is not an isolated example. Its vastness, along with the phenomena it exhibits, provides us with critical insights into the life cycles of galaxies, the birth and death of stars, and the mysteries surrounding the formation of supermassive black holes. M87's place at the center of the Virgo cluster, the largest cluster in our local supercluster, is especially significant, as it acts as a microcosm for the processes occurring in the broader universe. The Virgo cluster itself is a massive assembly of galaxies, containing over 2,000 galaxies. The cluster spans approximately 1.2 million light-years, and its gravitational pull binds the galaxies together. Within this structure, M87's central position makes it an anchor, a point of reference for understanding the interaction of galaxies within a cluster. The dynamics within clusters like Virgo are crucial for understanding how galaxies evolve and how they interact with one another through gravitational forces. M87's immense gravitational pull affects the orbits and motion of neighboring galaxies, contributing to the overall behavior of the cluster. In addition, it helps explain why some galaxies like M87 have been stripped of their gas, leading to a halt in new star formation, a phenomenon that is also observed in other galaxies across the cluster. Within the Virgo cluster, M87's interaction with its environment highlights one of the most intriguing features of galaxy evolution, the process of galaxy cannibalism. The central galaxy in a cluster, like M87, often has a history of consuming smaller galaxies. This process, called galactic mergers or cannibalism, is thought to play a critical role in the formation and growth of supermassive black holes. As galaxies collide, their gas, dust, and stars are pulled towards the central black hole, contributing to its growth. In fact, the large size of M87's supermassive black hole can likely be attributed to a long history of galactic mergers and accretion events. This process is not only responsible for the growth of black holes but also helps explain why some galaxies, particularly those in dense environments like clusters, become red and dead. These galaxies cease to form new stars and instead rely on older, more evolved stellar populations. One of the most fascinating features of M87 is the system of X-ray gas that surrounds the galaxy. The intracluster medium, ICM, is the hot, ionized gas that fills the space between galaxies in a cluster, and it plays a key role in shaping the evolution of galaxies within the cluster. M87's black hole is thought to interact with the ICM in a way that regulates the temperature and density of the gas, preventing it from cooling and condensing into new stars. This process, known as feedback, is crucial for the regulation of star formation in the galaxy. The energy released by M87's supermassive black hole, particularly from the relativistic jets, can heat the surrounding gas to temperatures that prevent it from cooling and forming stars. This type of galactic feedback is a key concept in understanding the life cycle of galaxies and the role of supermassive black holes in regulating the growth of galaxies across the universe. Another important feature of M87's black hole is the way it influences the surrounding environment through its relativistic jets. These jets are highly energetic outflows of material that are ejected from the black hole at nearly the speed of light. They can extend for millions of light years, affecting the intergalactic medium and other galaxies within the cluster. The jets from M87's black hole are particularly interesting because they serve as a natural laboratory for studying the behavior of matter in extreme conditions. The jets are composed of highly charged particles that are accelerated to relativistic speeds, creating a host of intriguing phenomena, including synchrotron radiation, which is emitted when charged particles travel near the speed of light in a magnetic field. The study of these jets, especially in the context of M87, provides valuable insights into the processes that occur in active galactic nuclei, AGN. These include the interaction of the jets with the intergalactic medium and their role in the regulation of star formation. The jets play a key role in galactic evolution by expelling energy into the surrounding environment, thereby influencing the conditions for future star formation. This feedback loop is essential for understanding how galaxies grow and change over time, and it is a process that is observed in many other active galaxies throughout the universe. Despite the significant strides we've made in understanding M87, it's important to recognize that many questions remain unanswered. For instance, while we know that supermassive black holes like the one in M87 grow by accreting matter, we still do not fully understand the detailed mechanisms that govern this process. How exactly do black holes accrete matter? What role does angular momentum play in this process? How do magnetic fields influence the accretion of gas and the formation of jets? These are questions that scientists are still grappling with. Advances in observational techniques, particularly with the advent of next-generation telescopes and observatories, will be critical in answering these questions. The Event Horizon Telescope, which made the groundbreaking observation of M87's supermassive black hole, will continue to be at the forefront of this research. With improvements in resolution and sensitivity, future observations will allow astronomers to peer even closer to the event horizon, the point beyond which nothing, not even light, can escape. These observations will likely provide new insights into the structure of the accretion disk, the behavior of matter near the black hole, and the mechanisms that drive the formation of relativistic jets. In addition to improving observational techniques, theoretical work will also play a key role in deepening our understanding of M87 and similar galaxies. The interplay between general relativity, quantum mechanics, and the study of black holes is one of the most exciting frontiers in modern astrophysics. Researchers are developing new models to explain the behavior of matter near black holes, including potential quantum effects that could influence the accretion process and the formation of black holes. These models will help us better understand the extreme environments near supermassive black holes and may provide answers to some of the most fundamental questions in physics. As we look beyond M87, it's clear that this galaxy is part of a much larger picture of cosmic evolution. The processes that shape galaxies like M87 are happening all around us in distant galaxies, and by studying objects like M87, we gain insight into the universal forces that govern the cosmos. Whether it's the formation of supermassive black holes, the behavior of relativistic jets, or the interactions between galaxies and clusters, M87 serves as a crucial piece of the puzzle in our understanding of the universe. Moreover, M87's significance extends into the realm of public interest and cultural impact. The first ever photograph of a black hole, released in 2019, captured the imagination of people around the world and brought attention to the mysteries of the universe. The image of M87's supermassive black hole became a symbol of human curiosity and achievement, inspiring a new generation of scientists, engineers, and astronomers to continue pushing the boundaries of knowledge. In many ways, M87 represents the cutting edge of scientific discovery. It is a galaxy that, by virtue of its extreme size, its massive black hole, and its dynamic role in the Virgo cluster, offers insights into the fundamental workings of the universe. As we continue to explore M87 and other galaxies like it, we will undoubtedly make new discoveries that challenge our understanding of the cosmos and redefine our place within it. Continuing our exploration of Messier 87, M87, it's essential to consider the implications of studying such a massive and complex system. As we've discussed, M87 provides a unique laboratory for understanding supermassive black holes, galaxy evolution, and the interactions that shape the fabric of the cosmos. However, as we delve deeper into the specifics, it becomes increasingly clear that M87 offers much more than just a fascinating glimpse into these phenomena. It represents a nexus where multiple lines of inquiry converge, giving rise to new perspectives on long-standing astrophysical questions. The discovery of the supermassive black hole at M87's core is, in many ways, just the tip of the iceberg. While the image captured by the Event Horizon Telescope, EHT, marked a historic moment in our understanding of black holes, it also opened the door to a multitude of new avenues for investigation. The image itself, though groundbreaking, is not the final answer but rather a springboard for future exploration into the mysteries of the universe's most enigmatic objects. The observation of M87's black hole, the first ever direct image of a black hole's event horizon, led to a remarkable shift in the way scientists approach the study of these objects. For decades, black holes existed primarily as theoretical constructs, their existence inferred from indirect evidence, such as the motion of stars around seemingly invisible objects, or the behavior of light in the vicinity of gravitational wells. The EHT's image provided visual confirmation of these invisible behemoths, marking a major milestone in our understanding of general relativity and the nature of spacetime itself. What the image revealed was a glowing ring of light, a distorted silhouette of the black hole's shadow surrounded by a bright accretion disk of hot gas and plasma. The disk of material, which spirals toward the black hole, appears brightly lit as it is heated to extreme temperatures due to the immense gravitational forces at play. This event horizon, the point of no return, defines the boundary beyond which nothing can escape, not even light. But what we now know is that this ring of light is not just a simple byproduct of black hole physics. It is a complex, multidimensional phenomenon that offers key insights into the behavior of matter, gravity, and even quantum effects at the highest energy scales. The study of M87's supermassive black hole continues to push the boundaries of both observational techniques and theoretical models. The EHT collaboration, which consists of dozens of institutions and scientists worldwide, is continuously working to improve the resolution of their observations. This is crucial because the image we currently have of the black hole is still relatively low in resolution. While it represents an unprecedented achievement, future enhancements to the EHT's capabilities will allow us to observe even finer details of the accretion disk, the jets, and perhaps even the inner workings of the black hole itself. Scientists hope that with higher resolution, we may be able to see structures within the accretion disk or gain new insights into the behavior of matter near the event horizon. One of the most exciting prospects of this research is the ability to probe the so-called black hole information paradox. According to current theories, information that falls into a black hole is lost to the outside universe, a concept that challenges our understanding of quantum mechanics. However, recent developments in theoretical physics, particularly in the realm of quantum gravity, suggest that black holes may not destroy information after all. Instead, the information may be encoded on the event horizon in a way that we do not yet fully understand. By studying the behavior of M87's black hole with greater precision, scientists hope to uncover more clues about this paradox and ultimately resolve the tension between quantum mechanics and general relativity. The role of M87 as an active galactic nucleus also presents an opportunity to study the broader cosmic phenomena that influence the structure and evolution of galaxies. The relativistic jets emanating from M87's supermassive black holes serve as a natural laboratory for studying high-energy astrophysics in extreme conditions. These jets, composed of highly energetic particles traveling close to the speed of light, extend vast distances into intergalactic space, influencing the surrounding environment and providing valuable insights into the processes that drive galaxy formation and evolution. The study of M87's jets, and the broader class of active galactic nuclei, AGN, has revolutionized our understanding of the connection between black holes and their host galaxies. It's now clear that the supermassive black holes at the centers of many galaxies are not just passive objects, but active participants in the shaping of their surroundings. The jets play a key role in regulating star formation within the galaxy by expelling energy and material into the intergalactic medium. This feedback loop, where the energy released by the black hole influences the environment and the rate of star formation, is a crucial process in galaxy evolution. It explains why some galaxies, like M87, appear to be quenched, with little or no new star formation taking place. But the influence of M87 extends beyond its immediate surroundings. As a member of the Virgo cluster, M87 is deeply embedded in the dynamics of one of the largest galactic clusters in the universe. The Virgo cluster contains thousands of galaxies, and M87 serves as the dominant galaxy in this environment. Its gravitational influence extends far beyond its own boundaries, affecting the orbits of neighboring galaxies and shaping the overall structure of the cluster. This makes M87 a key player in the study of galactic interactions and mergers. The Virgo cluster itself provides a fascinating context for understanding the behavior of galaxies within a dense, gravitationally bound environment. Galaxies and clusters like Virgo interact with each other in a variety of ways, from close gravitational encounters to full-on mergers. M87's position at the center of this cluster means that it has likely experienced multiple galactic collisions over the course of its long history. These interactions, particularly the accretion of material from smaller galaxies, contribute to the growth of M87's supermassive black hole and play a role in its overall evolution. Such interactions also help explain why M87 has a relatively low rate of star formation compared to other galaxies, as the cluster's dense environment has stripped away much of the gas needed for new stars to form. Looking at M87 in the broader context of galactic evolution and the study of galaxy clusters, we also see the importance of understanding the role that supermassive black holes play in regulating the growth of galaxies. The jets from M87's black hole, for example, can expel energy into the surrounding cluster, influencing the intracluster medium and preventing gas from cooling and condensing into new stars. This feedback mechanism is not just important for the evolution of M87 but for the entire Virgo cluster, as it helps regulate the overall star formation rate and affects the fate of galaxies within the cluster. The way that M87's black hole interacts with its environment highlights the interconnectedness of galaxies, black holes, and the larger cosmic structures they inhabit. These interactions are not isolated events but part of an ongoing, dynamic process that shapes the evolution of the universe. By studying galaxies like M87, we gain critical insights into the forces that govern the growth of galaxies, the formation of black holes, and the development of cosmic structures on the largest scales. As we look to the future, the continued study of Messier 87 promises to yield even more profound discoveries. The role of M87 as a key player in the evolution of the Virgo cluster, and its supermassive black hole as a crucial element in galactic dynamics will continue to be an area of intense research. With advancements in observational technology, such as the next generation of space-based and ground-based telescopes, we can expect to gather even more detailed data on M87's black hole, its accretion disk, and its relativistic jets. Through this research, we may uncover new aspects of the fundamental forces that govern the universe, from the behavior of matter near black holes to the ways in which galaxies interact and evolve over cosmic timescales. M87's unique characteristics as both a massive galaxy and a host to a supermassive black hole make it an indispensable object of study in the quest to understand the universe's deepest mysteries. In the grand scheme of things, the study of M87 represents not just an investigation into a single galaxy but a window into the very heart of cosmology itself. M87's black hole, estimated to have a mass of about 6.5 billion times that of our Sun, is so massive that it warps both space and time around it. The gravity near the event horizon is so intense that not even light can escape its pull, making it one of the most extreme objects known to physics. Observing it provided direct evidence of general relativity's predictions, but it also allowed researchers to begin examining how magnetic fields behave around black holes, how matter accretes onto these cosmic giants, and how jets of material can be launched at nearly the speed of light from the black hole's poles. These jets, like the one emerging from M87, are among the most powerful and energetic phenomena in the universe. Stretching for thousands of light-years into space, M87's jet has been studied extensively across all wavelengths of the electromagnetic spectrum: radio, optical, ultraviolet, X-ray, and gamma-ray. Each range offers a different glimpse into the processes at play within the jet. For instance, radio observations reveal the overall structure of the jet, showing how it bends and twists under the influence of magnetic fields. Optical and X-ray observations show the high-energy particles accelerated along the jet, revealing regions of intense shock where particles are pushed to near-light speeds. The origin of such jets is still a topic of active research. Current theories suggest that the intense magnetic fields generated by the swirling accretion disk around the black hole are crucial. These fields are thought to become twisted and collimated by the black hole's rotation, funneling material outward in tightly focused beams. Yet, the exact mechanisms by which these magnetic fields are organized and sustained are still not fully understood, and M87 provides a crucial testbed for developing and refining these theories. In addition to its black hole and jet, M87's stellar population offers important clues about its history and evolution. As an elliptical galaxy, M87 is dominated by older, redder stars, suggesting that it has not experienced significant star formation in recent times. This lack of young, blue stars indicates that M87's gas was consumed long ago or expelled during violent events like mergers. However, scattered throughout M87 are vast numbers of globular clusters, dense, spherical groups of stars that orbit the galaxy. M87 is particularly notable for its enormous population of globular clusters. Estimates suggest there could be over 12,000 globular clusters within its halo, vastly outnumbering the few hundred found in the Milky Way. These clusters are remnants from the early periods of galaxy formation, and their abundance hints at M87's tumultuous past. Scientists believe that M87 has grown to its current size by cannibalizing smaller galaxies, incorporating their stars, gas, and globular clusters into its own structure over billions of years. The galaxy's immense size and mass also mean it houses an enormous amount of dark matter. Dark matter, though invisible, exerts gravitational influence on visible matter, bending the paths of stars and light within the galaxy. Observations of the motions of stars and gas in M87 provide strong evidence for a massive dark matter halo enveloping the galaxy. Understanding how dark matter is distributed within galaxies like M87 is critical for solving one of the most enduring mysteries of modern cosmology: the nature and composition of dark matter itself. Moreover, M87's role within the Virgo cluster helps us understand how environment shapes galaxy evolution. In dense environments like clusters, galaxies experience interactions that are rare in more isolated regions of the universe. These interactions include gravitational encounters, mergers, and gas stripping, all of which can significantly alter a galaxy's structure and star formation activity. M87, sitting at the center of the cluster, is both a product and a driver of these interactions, influencing the fate of countless smaller galaxies in its vicinity. In the broader context of cosmic history, M87 offers a snapshot of galaxy evolution on the largest scales. From its early formation through countless mergers to its present-day grandeur, it embodies the processes that shaped galaxies over billions of years. Studying M87 helps scientists piece together the history of the universe, from the era of galaxy formation shortly after the Big Bang to the present-day large-scale structure we observe. Additionally, the study of M87 contributes to our understanding of cosmic magnetism. Magnetic fields play a crucial role in many astrophysical processes, from star formation to the dynamics of galaxy clusters, but their origins and behavior remain poorly understood. The magnetic fields in M87's jet, accretion disk, and surrounding environment provide a natural laboratory for investigating these phenomena under extreme conditions. At every scale, from the behavior of plasma near the event horizon of the black hole to the motion of galaxies within the Virgo cluster, M87 challenges and refines our understanding of the universe. Each observation leads to new questions, pushing the boundaries of astrophysics and driving the development of new technologies and theoretical models. As instruments and observational techniques continue to improve, future studies of M87 will no doubt uncover even more surprises. Projects like the Next Generation Event Horizon Telescope, more sensitive radio arrays, and space-based observatories will allow us to peer even deeper into the heart of this colossal galaxy, revealing details that are currently beyond our reach. Ultimately, M87 stands not just as a fascinating object in its own right but as a symbol of the vast, interconnected processes that govern the cosmos. Its black hole, its jet, its globular clusters, its role in the Virgo cluster, each aspect is a piece of a grand puzzle, offering glimpses into the fundamental workings of the universe. In M87, the sheer scale of the jet, extending some 5,000 light-years from the galaxy's center, is a testament to the extraordinary power unleashed by the supermassive black hole. This jet is not only visually striking but also serves as a beacon, signaling the processes occurring deep within the galaxy's heart. Studying it has allowed astronomers to infer properties of the magnetic fields and particle populations in the core region, offering clues about the fundamental physics governing accretion and jet formation. One fascinating aspect of the M87 jet is its apparent stability over vast distances. Despite traveling across thousands of light-years, the jet remains remarkably collimated, meaning it maintains a tight, narrow structure without dispersing significantly. This stability suggests that powerful magnetic fields are acting as a kind of containment system, keeping the jet focused even as it plows through the interstellar and intergalactic medium. Observations of the jet also reveal periodic knots and shocks, places where the material appears to brighten before continuing its journey outward. These features hint at dynamic processes within the jet, such as shock waves or regions of magnetic reconnection where particles are accelerated to even higher energies. Moreover, detailed observations have shown that the M87 jet exhibits apparent superluminal motion, the illusion that parts of the jet are moving faster than the speed of light. This phenomenon is not actually a violation of Einstein's laws but rather a perspective effect that occurs when objects move close to the speed of light in a direction close to our line of sight. It provides dramatic evidence of just how energetic and fast-moving the jet material is, and analyzing these motions allows astronomers to refine their models of jet physics and black hole activity. Beyond the jet, M87's broader galactic structure is equally impressive. Unlike spiral galaxies like our Milky Way, M87 is classified as a giant elliptical galaxy. Elliptical galaxies are characterized by their smooth, featureless light profiles, with stars distributed in a roughly spherical or ellipsoidal shape rather than a flattened disk. M87's stellar population is dominated by older, redder stars, indicating that the galaxy experienced a burst of star formation in the distant past but has since settled into a more quiescent phase. The lack of significant cold gas, the raw material for forming new stars, suggests that M87 has undergone processes that heated or expelled this gas, perhaps through interactions within the Virgo cluster or through the influence of its active nucleus. Another striking feature of M87 is its enormous halo of globular clusters. Globular clusters are tightly bound groups of tens of thousands to millions of stars, often among the oldest in the universe. M87 possesses an astonishing number of these clusters. Estimates range from about 12,000 to 15,000, far more than the few hundred found around the Milky Way. This vast population hints at a tumultuous past for M87, involving numerous mergers with smaller galaxies, each contributing their own complement of globular clusters to the larger galaxy. These mergers not only helped build up M87's massive size but also shaped its current structure and dynamics. In the halo surrounding M87, astronomers have also detected large amounts of dark matter, an invisible form of matter that does not emit or absorb light but exerts gravitational influence on visible matter. Measurements of the motions of stars and globular clusters orbiting in M87's outer regions indicate that much more mass is present than can be accounted for by the galaxy's stars and gas alone. This evidence for dark matter is consistent with findings in other galaxies and clusters and reinforces the idea that dark matter plays a fundamental role in the structure and evolution of the universe. M87's central region, dominated by the black hole and its associated phenomena, contrasts sharply with its vast, diffuse outskirts. The black hole's activity, particularly the launching of the relativistic jet, has a profound impact on the galaxy's environment. It injects enormous amounts of energy into the surrounding gas, creating shock waves and bubbles that can be observed in X-ray images of the galaxy. These feedback processes help regulate the cooling and condensation of gas, preventing excessive star formation and shaping the overall evolution of the galaxy. This mechanism, known as AGN, active galactic nucleus feedback, is thought to be a key factor in explaining why massive galaxies like M87 are typically quiescent and devoid of significant star-forming activity. On larger scales, M87's role within the Virgo cluster exemplifies the hierarchical nature of cosmic structure formation. Over billions of years, smaller galaxies and groups have fallen into the cluster, merging with larger systems and contributing to the growth of central giants like M87. These mergers are often violent events, tearing apart stars, gas, and dark matter halos, and redistributing material across vast distances. The remnants of these interactions can sometimes be seen as faint streams of stars or disrupted satellite galaxies orbiting the central giant. The study of M87 also sheds light on the behavior of intracluster gas, the hot, diffuse plasma that fills the space between galaxies in a cluster. Observations with X-ray telescopes reveal that the Virgo cluster's gas is not uniform but shows cavities and ripples, many of which are associated with the activity of M87's black hole. The jets and outbursts from the black hole inject energy into this medium, creating bubbles that rise buoyantly through the cluster gas and spread heat, preventing the gas from cooling and forming new stars. This interplay between the black hole, the galaxy, and the cluster environment illustrates the profound interconnectedness of cosmic structures across vastly different scales. As technology advances, astronomers continue to probe M87 in greater detail. Future observations with next-generation observatories like the James Webb Space Telescope, the Square Kilometre Array, and upgrades to the Event Horizon Telescope promise to reveal even more about this incredible galaxy. These studies aim to answer lingering questions about the nature of black holes, the formation and evolution of massive galaxies, and the role of feedback processes in shaping the cosmos. The story of M87 is far from complete. Each new discovery peels back another layer of mystery, revealing deeper complexities and raising new questions. As we continue to observe and analyze this colossal galaxy, we not only learn about its own unique properties but also gain invaluable insights into the broader workings of the universe. M87 stands as a cosmic monument to the power of gravity, the dynamism of galactic evolution, and the boundless curiosity that drives humanity to explore the stars. The study of the M87 jet has also led to important insights into the environments surrounding supermassive black holes. By analyzing the composition and behavior of the jet, astronomers have been able to probe the densities, temperatures, and magnetic conditions near the black hole. Observations indicate that the jet is composed of highly energetic electrons spiraling around magnetic field lines, emitting radiation through a process known as synchrotron emission. This type of radiation provides a powerful diagnostic tool for understanding the physical conditions not just near the black hole but also far out into the galaxy's halo and beyond. Furthermore, the immense energy output from the jet has profound effects on the galaxy itself. As the jet blasts through the interstellar medium, it injects energy into the surrounding gas, heating it and sometimes preventing it from cooling and collapsing into new stars. This process, known as feedback, is thought to play a critical role in regulating star formation within galaxies, helping to explain why massive galaxies like M87 have relatively low rates of new star birth compared to smaller, less active galaxies. In addition to the jet, M87's massive halo of hot gas is another significant feature. This halo extends for hundreds of thousands of light-years and is composed primarily of ionized hydrogen and other elements heated to millions of degrees Kelvin. X-ray observations have shown that this hot gas emits strongly, providing another window into the processes occurring within and around M87. The distribution and temperature of the gas offer clues about the galaxy's merger history, its gravitational interactions with neighboring galaxies in the Virgo cluster, and the ongoing activity of its central black hole. The environment of M87 is also littered with globular clusters, densely packed groups of old stars that orbit the galaxy in a vast halo. M87 hosts an extraordinary number of these clusters, far more than our own Milky Way. The presence of so many globular clusters hints at a rich history of galactic mergers and accretions, with each collision contributing to the growing swarm of clusters. Studying these globular clusters provides vital information about the early epochs of galaxy formation and the processes that led to the assembly of massive elliptical galaxies like M87. Moreover, the dark matter content of M87 is another key area of research. Like most galaxies, M87 is dominated by dark matter, an invisible and mysterious form of matter that does not emit, absorb, or reflect light. Its presence is inferred through its gravitational effects on visible matter, such as stars, gas, and globular clusters. By carefully measuring the motions of stars and clusters within M87, astronomers have been able to map out the distribution of dark matter within the galaxy. These measurements suggest that M87, like other massive galaxies, sits at the center of a vast and massive dark matter halo that extends far beyond the visible limits of the galaxy. The central role of M87 in the Virgo cluster is also of profound importance. As one of the dominant members of this cluster, M87 exerts significant gravitational influence over its neighbors. The Virgo cluster itself is the closest large cluster of galaxies to the Milky Way, containing thousands of member galaxies spread over millions of light-years. M87's gravity helps bind the cluster together, and interactions between M87 and other cluster members drive much of the dynamic activity observed within Virgo. These interactions can lead to galaxy mergers, tidal stripping of stars and gas, and the heating of the intra-cluster medium. On larger scales, studying M87 and the Virgo cluster contributes to our understanding of the cosmic web, the vast, filamentary structure of the universe formed by galaxies and clusters interconnected by threads of dark matter and gas. M87's location within this cosmic web provides a valuable data point for models of large-scale structure formation, helping to refine theories about how the universe evolved from a nearly uniform state after the Big Bang to the richly textured cosmos we see today. The black hole at the center of M87 also serves as a prime testing ground for fundamental physics. The ability to image the black hole's shadow offers unprecedented opportunities to test general relativity under extreme conditions. Any deviations from the expected shape or size of the shadow could hint at new physics beyond Einstein's theory, such as modifications to gravity on small scales, the presence of exotic matter, or even the influence of quantum gravitational effects. Moreover, continued observations of M87's black hole over time may reveal variability in the accretion flow and jet, offering insights into how these systems evolve on humanly observable timescales. Monitoring changes in the structure of the jet, fluctuations in brightness, or shifts in the shadow itself could provide clues about the dynamics of matter and magnetic fields near the event horizon, deepening our understanding of these enigmatic regions. Beyond astrophysics, M87 also captures the imagination because of what it symbolizes. It reminds us that the universe is filled with wonders far beyond the scale of human experience, objects so massive, energetic, and alien that they stretch our minds to comprehend them. M87's black hole, in particular, stands as a beacon of human curiosity and ingenuity, showing what can be achieved when scientists around the world unite to pursue a common goal. In many ways, the story of M87 is the story of modern astronomy itself, a story of incremental discoveries, technological innovation, and the relentless drive to explore the unknown. From the early optical observations revealing its fuzzy outline to the high-resolution imaging of its jet and black hole, each new advancement has peeled back another layer of mystery, revealing deeper truths about the cosmos and our place within it. As we continue to study M87, new instruments and missions will further enhance our understanding. The next generation of telescopes, such as the James Webb Space Telescope, the Extremely Large Telescope, and upgrades to the Event Horizon Telescope, will provide even sharper views of M87 and its environs. These facilities will allow astronomers to probe closer to the event horizon, measure the properties of the jet with greater precision, and map the galaxy's structure in unprecedented detail. Gravitational wave observatories like LIGO, Virgo, and the future LISA mission may also detect signals from interactions involving M87's black hole, such as mergers with other massive objects. These observations could open entirely new windows into the dynamic and often violent processes shaping galaxies and clusters. At the same time, theoretical work will continue to push the boundaries of our understanding, refining models of black hole accretion, jet formation, galaxy evolution, and cosmic structure. Simulations of black hole environments, carried out on some of the world's most powerful supercomputers, will grow increasingly realistic, offering new predictions to test against observations of M87. In the grand tapestry of the universe, M87 occupies a place of special significance, a cosmic giant whose influence extends across the electromagnetic spectrum, across the Virgo cluster, and across the minds of those who study it. It stands as a testament to the power of nature and the determination of humanity to understand that power, no matter how distant or daunting it may seem. The distribution and temperature of the gas offer clues about the dynamic history of M87, revealing evidence of past mergers, interactions with neighboring galaxies, and the powerful influence of its central black hole. Ripples, cavities, and shock fronts detected in the X-ray images suggest that episodic outbursts from the black hole have sent waves of energy rippling through the surrounding gas, much like the ripples created when a stone is tossed into a pond. These phenomena help scientists piece together a timeline of activity stretching back millions of years, painting a picture of a galaxy in constant, if slow, transformation. Another remarkable feature of M87 is its stellar population. The galaxy is home to hundreds of billions of stars, many of which are old and evolved, hinting at a long and complex history. Unlike spiral galaxies such as the Milky Way, M87 has very little cold gas and dust, meaning that star formation has largely ceased. Instead, its stellar light is dominated by ancient, reddish stars, remnants of an era when the galaxy was much younger and more active in creating new suns. Studies of these stars' motions and distributions have provided additional evidence for the enormous mass of the central black hole, as their orbits revealed the gravitational influence exerted by this invisible titan. M87 is also rich in globular clusters, densely packed spherical collections of tens of thousands to millions of stars. With more than 12,000 known globular clusters, M87 possesses far more than a typical galaxy of its size. These clusters are scattered across its halo, serving as ancient relics from the earliest periods of galaxy formation. By studying the ages, compositions, and motions of M87's globular clusters, astronomers can infer vital information about the galaxy's assembly history, including past mergers with smaller galaxies that may have contributed to its mass and size. Adding to the intrigue, M87 is situated at the very heart of the Virgo cluster, the nearest large cluster of galaxies to our own local group. The Virgo cluster contains thousands of galaxies, all gravitationally bound together in a sprawling cosmic city of stars. As the central galaxy, M87's immense gravitational pull dominates its surroundings, and it has likely grown to its current colossal size by cannibalizing smaller galaxies over billions of years. Observations of streams of stars and disrupted satellite galaxies around M87 provide direct evidence of these galactic meals, further underscoring the dynamic and violent nature of galaxy evolution. In recent years, continued observations of M87 have yielded ever more astonishing insights. Using very long baseline interferometry (VLBI) techniques, which link radio telescopes across the globe to create an Earth-size virtual telescope, astronomers have been able to peer with unprecedented detail into the very heart of the galaxy. These observations have allowed researchers to refine measurements of the black hole's properties, including its mass, spin, and orientation. They have also begun to test alternative theories of gravity, seeking any subtle deviations from Einstein's predictions that might hint at new physics. Even more excitingly, future missions promise to unlock even deeper secrets of M87. Planned upgrades to the Event Horizon Telescope network, as well as next-generation observatories such as the James Webb Space Telescope and the Extremely Large Telescope, will offer higher resolution, greater sensitivity, and broader spectral coverage. These advances will enable scientists to track the dynamics of the accretion disk and jet in real time, perhaps even observing changes in the black hole's appearance over the span of just a few years. Such observations could help answer some of the most profound questions in modern astrophysics. For example, what mechanisms determine the rate at which black holes grow? How are jets launched and sustained? What role do black holes play in shaping the galaxies and clusters around them? And could black holes like the one in M87 serve as laboratories for testing the limits of quantum mechanics and general relativity under conditions far beyond anything achievable on Earth? M87 stands as a beacon of cosmic mystery, a towering symbol of the immense forces that have sculpted our universe. It challenges our understanding, beckons our curiosity, and reminds us that for all our advances in science and technology, there are still vast realms of the cosmos that remain shrouded in darkness, waiting to be illuminated by the light of discovery. This astonishing number of globular clusters suggests a tumultuous past for M87, involving numerous mergers and acquisitions of smaller galaxies. Each merger likely contributed its own population of clusters to M87's growing collection, leaving behind a complex and layered structure within the galaxy. The distribution and motion of these clusters have provided astronomers with a valuable means of tracing M87's formation history, revealing that this behemoth grew not simply by forming stars internally, but by gravitationally consuming other galaxies over billions of years. In addition to its globular clusters, M87's surrounding halo of dark matter plays a crucial role in holding the galaxy together. Although invisible to telescopes, the presence of dark matter is inferred through its gravitational effects on the visible matter, such as stars and gas. Without the extra mass provided by dark matter, M87's outer regions would not have enough gravity to prevent stars and gas from drifting away into intergalactic space. This hidden scaffold of dark matter envelopes M87, influencing its structure and evolution in profound ways that are still the subject of intense study. M87's role within the Virgo cluster is another important aspect of its identity. As one of the cluster's most massive and dominant members, M87 sits at the cluster's center of gravity, anchoring the motions of hundreds of smaller galaxies that orbit around it. The cluster environment itself is a hotbed of galactic interactions, where collisions, tidal forces, and mergers are common. M87's gravitational pull influences the trajectories of nearby galaxies, shaping the cluster's overall structure and dynamics. On a cosmic scale, M87 also serves as a laboratory for testing fundamental physics, particularly our understanding of black holes. The Event Horizon Telescope's achievement in imaging M87's black hole was not just a triumph of observational astronomy, but also a critical test of Einstein's general theory of relativity. By capturing the shadow of the black hole and the surrounding emission ring, astronomers could directly compare the observed structure with theoretical predictions based on relativity. Remarkably, the observations matched expectations with stunning precision, providing some of the strongest empirical confirmation yet that general relativity remains valid even in the extreme gravitational environments near a supermassive black hole. Moreover, the black hole's apparent mass, as measured from the HT data, aligned closely with previous estimates derived from the motions of stars and gas near M87's core. This convergence of independent methods bolsters confidence in the tools astronomers use to weigh these cosmic giants. But the image also opened up new questions. For instance, the brightness of the ring was not perfectly uniform, suggesting complex dynamics in the material orbiting the black hole. Future observations aim to capture more detailed movies of the black hole's environment, potentially revealing swirling structures, magnetic fields, and the dynamics of matter plunging into oblivion. The techniques developed for the EHT have also inspired advances in imaging technology, data analysis, and international scientific collaboration. Synchronizing telescopes across continents to act as a single Earth-sized instrument required extraordinary precision, timing, and cooperation. In a sense, the effort to photograph M87's black hole represents humanity's ability to unify its intellectual and technological prowess to tackle some of the most profound mysteries of the cosmos. Beyond its technical achievements, M87 has captured the public imagination like few other astronomical objects. The iconic black hole image, with its fiery ring surrounding a dark void, became an instant symbol of cosmic mystery and human ingenuity. It inspired art, literature, and a renewed popular interest in astrophysics. M87 reminds us that while the universe is filled with strange and sometimes terrifying phenomena, it is also a source of endless wonder and inspiration, challenging us to expand our horizons and deepen our understanding of reality. Looking ahead, M87 will continue to be a focal point for astronomical research. Planned upgrades to the Event Horizon Telescope, including adding more observatories and improving resolution, promise even sharper images and movies of the black hole's immediate environment. These future observations could help unravel lingering questions about the nature of jets, the mechanics of accretion disks, and the behavior of matter under the most extreme conditions known. Meanwhile, other observatories, spanning the electromagnetic spectrum from radio waves to gamma rays, will keep probing M87's jet, halo, globular clusters, and interactions with the Virgo cluster. Each wavelength reveals a different layer of the galaxy's story, allowing astronomers to build an increasingly complete picture of this majestic cosmic structure. In addition, theoretical research inspired by M87's observations is leading to refinements in our understanding of black hole thermodynamics, information paradoxes, and even speculative ideas about quantum gravity. As a testbed for high-energy astrophysics and gravitational physics, M87 occupies a central position in the ongoing quest to unify the laws of the very large, governed by general relativity, with the laws of the very small, governed by quantum mechanics. But M87 is more than just a scientific specimen, it is a symbol of cosmic scale and grandeur. When we look at M87, We are peering across millions of light years and billions of years of history, touching the edges of what we can know and imagine. Its very existence challenges us to think bigger, to push the boundaries of knowledge, and to recognize our place in a vast and mysterious universe. The philosophical implications of studying M87 are profound. Standing on a small planet orbiting an average star in a relatively modest galaxy, we gaze outward at M87 and confront questions about existence, meaning, and our connection to the cosmos. Are supermassive black holes like the one in M87 common throughout the universe? What role do they play in shaping the galaxies we see? How does the universe organize itself into the breathtaking structures observed by our telescopes? Each question leads to more questions, weaving an endless tapestry of curiosity and exploration. In a way, M87 serves as both a mirror and a window. A mirror reflecting humanity's insatiable drive to understand, to explore, and to imagine. A window opening onto a realm where the familiar laws of physics bend and twist into strange new shapes, hinting at deeper truths yet to be uncovered. As our technological capabilities grow, and as new generations of astronomers turn their eyes toward M87 and galaxies beyond, we can expect even more breathtaking discoveries. From revealing the innermost secrets of black holes to mapping the grand architecture of galaxy clusters, M87 will remain a guiding light, or perhaps a guiding darkness, for all who seek to understand the universe's deepest mysteries. The lessons learned from this collaboration are now being applied to even more ambitious projects, including plans to create even sharper images of black holes by adding more telescopes to the global array and eventually placing instruments in space. By expanding the Event Horizon Telescope's reach beyond Earth, astronomers hope to bypass atmospheric interference entirely and achieve resolutions capable of revealing previously unseen details, such as the fine structure of black hole accretion flows and the behavior of magnetic fields on event horizon scales. These future observations could shed light on how black holes launch powerful jets, regulate galaxy growth, and perhaps even interact with dark matter. In the case of M87, further studies of its jet continue to fascinate scientists. The jet itself stretches thousands of light years into space and is composed of charged particles accelerated to near light speeds. How exactly the black hole extracts rotational energy to power such an immense feature remains one of astrophysics' most pressing mysteries. Theories propose mechanisms like the Blandford-Znajec process, where magnetic fields threading the spinning black hole extract energy and fling particles outward at relativistic speeds. Observations of the M87 jet across different wavelengths, radio, optical, X-ray, and gamma-ray, offer critical data to test these theories, providing a multidimensional view of the processes at play. The stability and apparent knot-like structures seen along the jet's length suggest interactions between magnetic fields and particle streams, leading to regions of compression and heating that glow brightly across the electromagnetic spectrum. High-resolution imaging has revealed that the base of the jet is astonishingly narrow, just a few times wider than the black hole itself, indicating that the jet is collimated, or focused, very close to the event horizon. This discovery ties into broader questions about how energy and angular momentum are extracted from black holes and transmitted across cosmic distances. Another striking feature of M87's influence is its impact on the surrounding intergalactic medium. The energy and particles ejected by the jet do not simply vanish into space. They interact with the hot, tenuous gas filling the Virgo cluster. These interactions create shock waves, heat the cluster gas, and prevent it from cooling and forming new stars in large quantities, a process known as feedback. Feedback mechanisms are critical in modern galaxy formation models, explaining why the largest galaxies do not endlessly grow through unchecked star formation. M87, with its powerful jet and massive black hole, offers a prime example of how feedback operates on grand scales, regulating both its own evolution and that of its environment. Despite all that has been learned about M87, much remains shrouded in mystery. For example, the exact composition of the jet, whether it is dominated by electrons and positrons or by heavier particles like protons, is still debated. Similarly, the precise way magnetic fields are structured and maintained within the jet remains unclear. Unraveling these mysteries will require even more detailed observations, more sophisticated simulations, and perhaps entirely new theories. M87's black hole, jet, globular clusters, halo of hot gas, dark matter, and its role in the Virgo cluster weave a story that extends beyond a single galaxy. It touches on the evolution of cosmic structures, the nature of gravity, the life cycle of galaxies, and the extreme physics operating at the universe's most enigmatic frontiers. In many ways, M87 stands as a cosmic Rosetta Stone, a key to deciphering the language of the universe on its largest and most extreme scales. The sheer scale of M87 itself is humbling. Its mass dwarfs that of the Milky Way, its halo stretches over hundreds of thousands of light years, and its gravitational influence can be felt across much of the Virgo cluster. This immense presence reminds us that while our own galaxy feels vast to us, it is but a small and relatively modest structure in the grand tapestry of the cosmos. Studying M87 allows us to glimpse the forces and phenomena that shape not just individual galaxies, but entire clusters and perhaps even the large-scale structure of the universe. Observations of M87 also intersect with cosmology, the study of the universe's origin, structure, and eventual fate. By examining how galaxies like M87 formed and evolved, astronomers can test models of cosmic evolution, the behavior of dark matter, and the role of supermassive black holes in shaping the early universe. M87's enormous mass and central location within the Virgo cluster make it a valuable probe of the distribution of matter on cluster scales, offering insights into how galaxies gather into larger structures over billions of years. In addition to professional research, M87 has inspired generations of amateur astronomers and stargazers. Visible even through modest backyard telescopes under dark skies, it appears as a faint, elliptical smudge, a humble sight that belies its extraordinary nature. For many, seeing M87 firsthand sparks a sense of wonder and curiosity about the universe's vastness and the hidden forces at work within it. Public fascination with M87 soared to new heights following the release of the EHT black hole image, making this once obscure galaxy a symbol of human discovery and cosmic mystery. The future promises even greater revelations. Projects like the Next Generation Event Horizon Telescope, the James Webb Space Telescope, and large ground-based observatories like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will all bring unprecedented capabilities to bear on M87 and its surroundings. These instruments will allow astronomers to probe deeper into the galaxy's core, resolve finer details of the jet, map the dark matter distribution with greater accuracy, and perhaps even detect signs of new physics at play. As technology advances, so too does our ability to peer into the heart of M87 and understand the forces that have shaped it across cosmic time. With each new discovery, our picture of this colossal galaxy grows richer and more intricate, revealing not just the story of a single galaxy, but insights into the fundamental workings of the universe itself. M87 is not merely an object of study, it is a gateway to understanding the cosmos on scales both grand and minute. Superluminal motion provides further evidence that the jet's particles are traveling at velocities incredibly close to the speed of light, reinforcing the extreme and energetic nature of the processes occurring near M87's central black hole. Detailed monitoring of the jet over years has allowed scientists to track individual knots of material as they move outward, offering a dynamic glimpse into the ongoing activity within the galaxy's core. Variations in brightness, apparent shifts in position, and changes in the jet's structure over time have revealed the interplay between magnetic fields, shock waves, and relativistic particles. The jet is also notable for its polarization, meaning the light emitted by the jet is aligned in a specific direction, a clear signature of strong magnetic fields. By studying the polarization properties, astronomers can infer the configuration and strength of these magnetic fields, which play a crucial role in shaping the jet's structure and controlling the acceleration of particles. Recent observations have shown that the magnetic fields near the base of the jet are incredibly well-ordered, suggesting that magnetic processes are critical not only in launching the jet but also in maintaining its coherence over vast distances. In addition to its bright, well-known jet, M87 also possesses a counterjet, which is much fainter and harder to detect. This counterjet points in the opposite direction but is much less visible because of relativistic beaming, an effect where material moving toward us appears much brighter than material moving away. The existence of a counterjet offers further clues about the three-dimensional geometry of the system and the angle at which we are viewing it, adding important constraints to models of the black hole and its environment. Beyond its spectacular jet, M87 is also surrounded by an extended halo of diffuse light, made up of stars that have been stripped from smaller galaxies through gravitational interactions over billions of years. This stellar halo stretches far beyond the visible confines of the galaxy, and represents a fossil record of M87's cannibalistic past. Studying the properties of this halo, its density, composition, and kinematics, provides vital insights into the history of galaxy mergers and the processes that shape the giant elliptical we observe today. The halo is not uniform. It contains streams and shells of stars that hint at relatively recent mergers. These features are the remnants of disrupted galaxies, stretched out and smeared across the sky by M87's immense gravitational field. By mapping these structures, astronomers can reconstruct the orbits and properties of the progenitor galaxies, offering a glimpse into the dynamic and often violent life of a massive galaxy at the center of a cluster. The presence of such a massive black hole at the heart of M87, coupled with the galaxy's enormous size and extended halo, raises important questions about the coevolution of galaxies and black holes. Evidence suggests that the growth of supermassive black holes and the galaxies they inhabit are closely linked. Feedback from active galactic nuclei, such as powerful jets and radiation from the black hole, can regulate star formation by heating or expelling gas, thus influencing the growth of the galaxy itself. M87 serves as a prime example of this interconnected relationship, where the energy output from the black hole has a profound impact on the galaxy and its environment. Indeed, M87's central black hole likely plays a key role in shaping the intracluster medium, the hot, diffuse gas that fills the Virgo cluster. Observations in X-ray wavelengths reveal cavities and ripples in this gas, interpreted as the result of outbursts from the black hole. As the black hole periodically releases enormous amounts of energy, it inflates bubbles in the surrounding gas, which then rise buoyantly and distribute heat throughout the cluster. This process, known as AGN feedback, helps prevent the gas from cooling too quickly and forming stars at an unsustainable rate. Understanding AGN feedback in systems like M87 is crucial for explaining why the universe looks the way it does today. Without such feedback mechanisms, models predict that galaxies would form too many stars too quickly, resulting in a cosmos filled with overly massive and bright galaxies. The relatively modest star formation rates observed in massive galaxies like M87 suggest that black holes, despite being tiny compared to their host galaxies, exert a powerful influence over cosmic evolution. The study of M87's black hole, jet, and galaxy as a whole continues to be a central focus of modern astrophysics, offering invaluable clues about the most fundamental processes shaping the universe. With each new observation, from radio to gamma-ray wavelengths, astronomers peel back another layer of mystery, moving closer to a full understanding of how such colossal structures form, evolve, and influence their surroundings. Yet, despite all we have learned, M87 still holds many secrets. The exact mechanisms by which black holes launch jets, the detailed structure of the magnetic fields near the event horizon, the history encoded in the faintest reaches of the stellar halo, all remain active areas of research. Future missions, both ground-based and spaceborne, promise to bring sharper images, deeper surveys, and more precise measurements that will continue to transform our understanding of this extraordinary galaxy. Even as we look forward to these advances, M87 reminds us that the universe is vast, ancient, and filled with wonders beyond our current comprehension. It stands as a testament to the power of curiosity and the incredible ingenuity of human beings who, armed with little more than telescopes and theories, have managed to glimpse the workings of the cosmos on its grandest scales. In every photon captured from M87, whether from its brilliant core, its sweeping jet, or its ghostly halo, we find a story written across billions of years, a cosmic epic that continues to unfold with each new discovery. M87 remains a powerful symbol of our quest to understand the universe, and each new chapter of its study brings us closer to unlocking the deepest secrets of space, time, and the forces that govern them. Even as we continue to study the details of its black hole, its jet, and its surrounding environment, M87's role as a cosmic laboratory for testing the limits of our knowledge is just beginning. The galaxy itself is a crucible in which some of the most important physical theories are being tested, from the behavior of matter under extreme gravitational conditions to the nature of dark matter and dark energy. As we delve deeper into the study of M87, one of the most intriguing aspects of this galaxy is the way it exemplifies the complexities of galaxy formation and evolution. The central black hole at M87's core is not just a passive bystander in the galaxy's development. It is an active participant, influencing the galaxy's structure and the behavior of the materials surrounding it. The processes occurring in the heart of M87 offer vital clues to understanding how supermassive black holes shape the evolution of galaxies and the cosmic environment at large. One fascinating aspect of M87's black hole is how it is thought to have formed. While many supermassive black holes are believed to have grown through the accretion of gas and mergers with other black holes, the specific details of M87's formation remain elusive. Did it grow through the slow accumulation of matter over billions of years, or was its rapid growth triggered by a major cosmic event, such as a galaxy merger or an influx of gas from the surrounding cluster? These are questions that scientists are still grappling with. By studying the black hole's environment and the remnants of past galactic interactions, we may eventually be able to piece together the history of M87's central supermassive black hole and how it has evolved to its current state. The influence of M87's central black hole extends beyond the confines of its own galaxy. As the dominant member of the Virgo cluster, M87 exerts a profound gravitational influence on the cluster as a whole. The Virgo cluster, which contains thousands of galaxies, is held together by the combined gravitational pull of its constituent galaxies and the central supermassive black hole. The dynamic interactions between galaxies in the cluster, including galaxy mergers and gravitational interactions, are governed in large part by the presence of this massive black hole at the cluster's center. In fact, the structure and dynamics of the Virgo cluster are closely tied to M87's black hole. One of the most compelling observations in this regard is the presence of the intracluster medium, a vast, hot gas that permeates the cluster and is heated by the energy emitted from the central black hole. This hot gas is responsible for the X-ray emission observed in the cluster, and it plays a crucial role in regulating the rate of star formation in the cluster's galaxies. The feedback from M87's black hole, in the form of jets and radiation, helps to prevent the gas from cooling too rapidly, thus ensuring that the rate of star formation in the cluster remains relatively low. This mechanism, known as AGN feedback, is a key process in understanding the evolution of galaxy clusters. In addition to the influence of M87's black hole on the cluster, the galaxy itself is a remarkable example of the intricate interplay between gravitational forces and cosmic evolution. M87's history as a giant elliptical galaxy suggests that it has undergone numerous mergers with smaller galaxies over billions of years. These mergers have shaped its current structure, which is dominated by an enormous bulge of stars and a diffuse stellar halo. The stellar population in M87 is old and relatively low in metallicity, indicating that the galaxy formed early in the history of the universe. However, the study of M87's stellar halo reveals more than just the history of the galaxy itself. The halo contains evidence of the cannibalization of smaller galaxies, with streams of stars that have been pulled from their original galaxies and incorporated into M87's vast stellar envelope. These stellar streams provide a snapshot of the galaxy's past mergers, offering a unique opportunity to trace the orbital histories of the galaxies that M87 has absorbed. This process of galactic cannibalism is thought to be a common feature in the evolution of massive elliptical galaxies and plays a crucial role in their growth and development over cosmic time. Beyond its immediate environment, M87 also serves as a key target for understanding the larger-scale structure of the universe. As a giant galaxy at the center of the Virgo cluster, M87 offers a unique vantage point for studying the effects of cluster dynamics on galaxy evolution. The Virgo cluster itself is part of a larger cosmic structure known as the Laniakea supercluster, which contains thousands of galaxies and spans hundreds of millions of light-years. The study of M87 and its role within the Virgo cluster provides valuable insights into how galaxy clusters form and evolve over time, and how the gravitational interactions within these clusters shape the galaxies they contain. The complexity of M87's structure is also reflected in the detailed mapping of its dark matter distribution. Like many other large galaxies, M87 is thought to contain a significant amount of dark matter, an invisible and mysterious substance that makes up the majority of the galaxy's mass. By studying the motion of stars and gas in the outskirts of the galaxy, astronomers can infer the distribution of dark matter and gain insights into its properties. M87's dark matter halo is thought to be one of the most massive and extended known, and it plays a crucial role in the galaxy's overall dynamics. The study of dark matter in M87, and in galaxies like it, is a critical piece of the puzzle in understanding the nature of dark matter itself, which remains one of the most profound mysteries in modern astrophysics. In the quest to understand M87, astronomers have also turned to simulations and theoretical models to explore the processes occurring within this extraordinary galaxy. These models aim to reproduce the observed features of M87, including its black hole, its jet, and its stellar population, by simulating the complex interactions between gravity, magnetism, gas, and stars. The results of these simulations provide a theoretical framework for interpreting the vast amounts of observational data gathered from M87 and its surroundings. As our computational capabilities continue to improve, these simulations will become increasingly sophisticated, allowing for more detailed and accurate models of M87's evolution. One area of particular interest is the study of the black hole's accretion disk, the swirling disk of gas and dust that feeds the black hole. As material spirals inward toward the event horizon, it is heated to extremely high temperatures, emitting intense radiation across the electromagnetic spectrum. Observing the behavior of the accretion disk can provide valuable information about the physical properties of the black hole, such as its mass, spin, and the structure of its event horizon. In addition, the accretion disk is thought to be a key component in the launch of the powerful jets observed in M87. Understanding how this disk works and how it connects to the black hole's jet is one of the central goals of modern astrophysical research. As we continue to explore M87, we are reminded of the extraordinary nature of this galaxy and the immense scale of the universe in which it resides. M87 is not only a fascinating object in its own right, but it also serves as a laboratory for studying the fundamental processes that govern the cosmos. From the behavior of supermassive black holes to the interactions between galaxies and their clusters, M87 offers us a window into the deepest mysteries of the universe. The insights gained from studying this galaxy will undoubtedly shape our understanding of the cosmos for many years to come. M87 continues to be an essential puzzle piece in the grand cosmic landscape. The wealth of knowledge it provides transcends just the understanding of black holes and galaxy formation. It touches on the fundamental nature of spacetime, gravity, and even the birth and death of stars. The detailed study of M87 will influence not only astronomy but also the way we comprehend the universe at its most extreme and enigmatic scales. Beyond the event horizon of M87's central black hole lies a region where the laws of physics, as we currently understand them, begin to break down. This boundary, where gravity is so intense that not even light can escape, challenges our understanding of spacetime itself. The Event Horizon Telescope's groundbreaking imaging of M87's black hole gave us a first look at this cosmic boundary, presenting a visual representation of the mysterious region where gravitational forces become so strong that they warp spacetime. For the first time, astronomers were able to directly observe the shadow cast by the black hole's event horizon, offering us a glimpse into this enigmatic world where the laws of physics, as we know them, are pushed to their limits. This observation was a culmination of decades of work, harnessing the power of radio telescopes located around the globe, effectively turning the Earth into a giant virtual telescope. The resulting image was a triumph for modern science, validating the predictions of Albert Einstein's theory of general relativity and opening up new possibilities for understanding black holes in ways never before thought possible. M87's black hole has since become one of the most famous objects in the universe, not just for its size and power but also for the unique opportunity it provides to test fundamental theories of physics. The nature of the black hole at M87's core raises several critical questions about the very fabric of the universe. What happens inside the event horizon? Can anything escape once it passes the point of no return? These questions push the boundaries of our understanding of quantum mechanics, and in particular, the so-called information paradox. According to classical physics, all the matter that falls into a black hole is lost to the universe. However, quantum mechanics suggests that information about the matter should not be completely lost but rather encoded in some way, possibly on the event horizon itself. M87's black hole may offer the perfect testbed for resolving this paradox, as astronomers continue to observe and gather data on the behavior of material around it. Another tantalizing aspect of M87 is the jet that emanates from its center. This powerful stream of high-energy particles, shot out into space at nearly the speed of light, is one of the most spectacular phenomena in the universe. These jets have been a subject of intense study for decades, but their origin and mechanics are still not fully understood. The jet's origin is closely tied to the properties of the accretion disk around the black hole, as well as the complex magnetic fields that are present. Some scientists believe that these magnetic fields play a crucial role in accelerating the particles in the jet to such extreme speeds. The black hole's spin and the alignment of its magnetic field are thought to play a key role in shaping the jet. A rapidly spinning black hole, in combination with the magnetic fields generated by the accretion disk, could create a funnel-like structure that channels the high-energy particles outward. However, the exact mechanisms behind this process remain a topic of active research. Recent studies, along with simulations, are beginning to shed light on how this powerful jet is produced, with some theorists suggesting that the jet may be driven by the transfer of angular momentum from the black hole itself. One of the remarkable features of M87's jet is its sheer scale. The jet stretches out for thousands of light years, far beyond the immediate vicinity of the black hole. The observation of such a large-scale jet offers astronomers the opportunity to study the interaction between black holes and the surrounding environment over vast distances. These jets also provide a glimpse into the processes that might occur in other galaxies with active galactic nuclei, where black holes play a central role in shaping the galaxy's evolution. M87 is not just significant for its black hole, or its jet, but also for its position in the broader cosmic context. It resides in the heart of the Virgo cluster, one of the largest and most studied galaxy clusters in the universe. The dynamics within this cluster provide important clues about the evolution of galaxies and their interactions. Within the Virgo cluster, M87 is considered the dominant galaxy, both in terms of mass and influence. Its central role in shaping the cluster is an essential factor in understanding the long-term evolution of galaxy clusters and the complex processes that govern them. The interactions between M87 and the other galaxies in the Virgo cluster are a testament to the complex gravitational dance that occurs within galaxy clusters. Over billions of years, M87 has collided and merged with numerous smaller galaxies, a process that has significantly altered its structure. This galactic cannibalism, where larger galaxies consume smaller ones, is not unique to M87, but its prominence in the Virgo cluster makes it a crucial case study for understanding how galaxies grow and evolve over time. Interestingly, M87 is also notable for its relatively isolated position within the Virgo cluster. While it interacts with neighboring galaxies, its central black hole seems to be a beacon in an otherwise dynamic and turbulent environment. This isolation offers an intriguing contrast to the denser regions of the cluster, where galaxy interactions are more frequent, and the gas between galaxies is heated by powerful interactions. In this sense, M87 represents a sort of cosmic anchor, standing firm in the center of the cluster, while the surrounding galaxies experience much more violent interactions. One of the most fascinating aspects of M87 is the dark matter that surrounds it. Dark matter, which makes up a significant portion of the universe's mass, remains invisible and detectable only through its gravitational influence on visible matter. M87's dark matter halo is one of the most massive and extended known, playing a critical role in the galaxy's overall structure and dynamics. The presence of dark matter is inferred from the motion of stars and gas in the galaxy, which move much faster than would be expected based on the visible matter alone. This observation suggests the existence of a vast, invisible mass surrounding the galaxy, a mass that cannot be seen directly but whose presence is undeniable. The study of dark matter in galaxies like M87 is crucial for understanding the broader cosmic structure. Dark matter is thought to be the scaffolding upon which galaxies and galaxy clusters are built. It exerts a gravitational pull that helps to bind galaxies together, preventing them from flying apart due to the motion of their stars. Without dark matter, the formation of galaxies and clusters would not be possible in the way we observe them today. The influence of M87's central black hole on the surrounding cluster goes beyond the realm of gravitational interactions. The high-energy radiation emitted by the black hole's accretion disk and the jets also plays a crucial role in the behavior of the intra-cluster medium. This gas, which fills the space between galaxies in the cluster, is heated by the energy emitted from M87's black hole, creating a hot, diffuse atmosphere that pervades the cluster. This heating process helps to maintain the overall stability of the cluster, preventing the gas from cooling and condensing into new stars. In this sense, M87's black hole acts as a cosmic regulator, controlling the rate of star formation and influencing the evolution of the entire cluster. As we look to the future, the study of M87 and its black hole will continue to be at the forefront of astronomical research. With advanced technologies like the James Webb Space Telescope and further developments in ground-based observatories, we are likely to gain even more insights into the mysteries surrounding this galaxy. M87's central black hole offers a unique opportunity to study the most extreme environments in the universe, providing a crucial testing ground for theories of gravity, quantum mechanics, and the nature of dark matter. The discoveries made in M87 are not only advancing our understanding of black holes and galaxies, but are also reshaping our conception of the universe itself. The study of this fascinating galaxy and its black hole represents one of the most exciting frontiers in modern science, offering the promise of even more groundbreaking revelations in the years to come. As we continue to peer deeper into the heart of M87, we can be sure that this remarkable galaxy will continue to unlock the secrets of the cosmos, guiding us toward a deeper and more profound understanding of the universe in which we live. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.